जितनी बेहतर आपकी मेथोडोलॉजी होगी, उतनी ही बेहतर मेट्रोलॉजी होगी। और जितनी विश्वसनीय मेट्रोलॉजी जिस देश की होगी, उस देश की विश्वसनीयता दुनिया में उतनी ही ज्यादा होगी।
The concern for establishing a rational and universal set of measurement units led to a landmark meter convention on May 20th, 1875, where an international diplomatic treaty was signed by 17 nations in Paris. This convention brought the world's focus on metrology that resulted in an international structure to ensure that all member states have equivalent capabilities on measurements. This treaty founded the International Bureau of Weights and Measures, BIPM, in Paris, France, under the authority of the General Conference on Weights and Measures, CGPM. At present, CGPM has 62 member states and observers from 40 associate states and economies. To commemorate the signature of the Meter Convention, the World Metrology Day is celebrated on 20th of May every year. CSIR India was established on September 26, 1942, under the leadership of Sir Shanti Sarup Bhatnagar. In 1943, the governing body of CSIR decided to establish 5 national laboratories, including National Physical Laboratory (NPL). The foundation of NPL was laid on January 4, 1947 by Pandit Jawaharlal Nehru, about 7 months before India became independent. The CSIR NPL was expected to fill a wide gap in the scientific and industrial organizations of India. It is mandated to maintain the standards and to undertake research for achieving a high degree of accuracy in the measurements. It establishes international equivalence through intercomparisons with other NMIs of the world. The present campus of CSIR NPL was inaugurated by former Deputy Prime Minister Sardar Vallabhbhai Patel on 21st January 1950. The inaugural ceremony of CSIR NPL was attended by a galaxy of eminent people from many countries. It is apparent that the world had very high expectations from the CSIR NPL towards the growth of India. The Standards of Weights and Measures Act, enacted by the Government of India in 1956, ensures that each of its citizens has an access to uniform measurements that are traceable to the SI units. The Republic of India signed the diplomatic treaty and became the member state of CGPM in 1957. With CSIR NPL as its National Metrology Institute NMI, CSIR NPL is the founding member of Asia Pacific Metrology Program, APMP, which is one of the 6 regional metrology organizations, RMOs, of the world. On 16th November 2018, during the 26th CGPM meeting held at Versailles, France, 60 member states voted for a landmark revision of the SI units. On behalf of India, a team led by Dr. D.K. Aswan, Director, CSIR NPL, voted for the revision of the SI units. On May 20th, 2019, CSIR NPL implemented the revised SI units in India. The Legal Metrology National Standards Rules 2011 under Chapter 3 states, the work relating to the realization, establishment, custody, maintenance, determination, reproduction and updating of national standards of weights and measures shall, on the commencement of these rules, be the responsibility of the National Physical Laboratory. Therefore, this is the core mandate of CSIR NPL. CSIR NPL is mandated to be India's NMI by an Act of Parliament. Being the custodian of national standards of measurements, CSIR NPL is responsible for the realization, establishment, upgradation, maintenance, and dissemination of standards at par to international level, providing metrological traceability across the country. The mandate of CSIR NPL is to ensure the realizations of SI units as national standards and to transfer the values of the standards to the national quality infrastructure through calibrations, testing, and other measurement-related services. The customers who are the direct beneficiaries of CSIR NPL make their measurement result traceable to those of CSIR NPL and hence to the SI units. These organizations in turn provide measurement services to their customers, hence assuring quality in the measurements across the country. CSIR NPL is also Timekeeper of India. CSIR NPL, through its primary national calibration facilities, supports thousands of quality assurance testing and calibration laboratories across the country, which belong to the government, strategic sector, and industries. The scientific endeavor of CSIR NPL embarked with the invention of indelible ink, which is being used for impartial execution of the electoral process of India. CSIR NPL also developed hermetically sealed boxes of tempered glass for safe preservation and maintenance of original copy of the Constitution of India and still discharging this constitutional safeguard duty. CSIR NPL also plays vital role in nation building through its path-breaking scientific contributions, which have wider socio-economic applications covering research and development of new and strategic materials to environmental assessment and protection. At present, CSIR NPL is carrying out its mandate through 6 divisions.
This division has a mandate to realize, establish, upgrade, maintain, and disseminate standards for various physico-mechanical parameters. These include 4 SI units of mass, length, temperature, and luminous intensity, and many drive parameters like volume, density, viscosity, humidity, and moisture content. It provides national service of calibration, testing, consultancy, and advice to the various government bodies. It also provides training to generate the skilled manpower in the country and SAARC nations. Physico-mechanical metrology division issues more than 2,000 calibration and test reports annually to industry and various user organizations.
Electrical and Electronics Metrology.
Electrical and Electronics Metrology Division is the custodian of national standards and disseminating traceability to electrical and electronics parameters, which involves voltage, current, resistance, power, and energy, and quantum standards at international level. Apex level calibration and testing services are provided to various manufacturers, power sectors, strategic sectors to enhance manufacturing and exports. R&D in metrology is going on towards quantum standards for realization of quantum current, quantum resistance, quantum nanophotonics. The division also contributing in resolving various industrial and societal issues and challenges from time to time for benefits of industries and society.
Advanced Materials and Device Metrology.
This division consists of 4 activities: photovoltaic materials, photonic materials, advanced carbon product, and solar energy complex. The photovoltaic section working on MR pulse, micro and nanocrystalline silicon, thin film material for solar cell application. Also developing the quality infrastructure for material and device testing like primary standard for solar cell, including validation of solar cell performance. Group is also working on the agriculture waste management, recycling of solar cell, plastic waste. Recently, activated carbon from waste juice stick has been developed, which had so many applications for daily life.
साथियों, आज का भारत पर्यावरण की दिशा में दुनिया का नेतृत्व करने की तरफ बढ़ रहा है, लेकिन एयर क्वालिटी और एमिशन को मापने की टेक्नोलॉजी से लेकर टूल्स तक हम दूसरों पर निर्भर रहे। आज इसमें भी आत्मनिर्भरता के लिए हमने एक बड़ा कदम उठाया है। इससे भारत में प्रदूषण से निपटने के लिए ज्यादा सस्ते और प्रभावी सिस्टम तो विकसित ही होंगे, साथ में एयर क्वालिटी और एमिशन से जुड़ी टेक्नोलॉजी के ग्लोबल मार्केट में भी भारत की हिस्सेदारी बढ़ जाएगी। हमारे वैज्ञानिकों के ही सतत प्रयासों से भारत आज ये उपलब्धि हासिल कर रहा है।
Environmental Sciences and Biomedical Metrology.
The Environmental Sciences and Biomedical Metrology Division is engaged in the frontline research in the areas of ionospheric and atmospheric sciences like climate change, radiative forcing, air quality, etc. Besides sensors development and biomedical, division is working to establish test calibration and certification facility for the air pollution monitoring equipments like aerosol samplers, continuous ambient air quality monitoring system, and the online continuous emission monitoring system at CSR NPL to cater to the requirement of various stakeholders like government, regulators, manufacturers, and users. The research activities in the division span from the understanding of chemical and physical properties of the upper and lower atmosphere to the development of sensor materials and devices for environmental and biomedical applications.
जिस भारतीय निर्देशक का लोकार्पण किया गया है, यह हमारे उद्योग जगत को क्वालिटी प्रोडक्ट्स बनाने के लिए प्रोत्साहित करेगा। अब फूड, एडिबल ऑयल्स, मिनरल्स, हेवी मेटल्स, पेस्टिसाइड, फार्मा और टेक्सटाइल ऐसे अनेक क्षेत्रों में अपने सर्टिफाइड रेफरेंस मटेरियल सिस्टम को मजबूत करने की तरफ हम तेजी से आगे बढ़ रहे हैं। अब हम उस स्थिति की तरफ बढ़ रहे हैं जहां इंडस्ट्री रेगुलेशन सेंट्रिक अप्रोच के बजाय कंज्यूमर ओरिएंटेड अप्रोच की तरफ बढ़े। इन नए मानकों से देश भर के जिलों में वहां के लोकल प्रोडक्ट को ग्लोबल पहचान दिलाने का अभियान है। उसको बहुत लाभ मिलेगा। इससे हमारे
Let's have a big round of applause as our dignitaries are entering the auditorium. Everyone kindly be seated and we'll begin the inaugural function soon. Kindly maintain physical distancing and wear your masks properly to maintain the COVID-19 protocol. Now let's begin our inaugural function. I would like to invite the dignitaries on stage. The Honorable Minister, Dr. Jitendra Singh, Minister of State of the Ministry of Science and Technology, Ministry of Earth Sciences, Ministry of Personnel, Public Grievances and Pensions, Department of Atomic Energy, and the Department of Space, Government of India. The Director General of CSIR and also the Secretary of DSIR, Dr. Shekhar C. Mande. The Postmaster General Operations, Delhi Circle, the Department of India Post, Shri Ashok Kumar, along with the respected Director of NPL, Professor Venu Gopal Achanta. I would also like to invite Dr. Shemendra Sharma, Chief Scientist of CSIR NPL and the Chairman of the Organizing Committee of the Platinum Jubilee Year celebration. It gives us immense pleasure that to commemorate 75 years of CSIR NPL, we have such amazing dignitaries on the dais with us. Now, I would like to request Dr. Kriti to felicitate our Honorable Minister with a floral bouquet. Let's have a big round of applause, everyone. Thank you. I would like to request Dr. Avni to kindly felicitate the Director General with a floral bouquet. A big round of applause, everyone. And I would like to request Dr. Komal to felicitate Sri Ashok Kumar with a floral bouquet. Thank you so much. Everyone kindly be seated. Now, light is the symbol of knowledge, and let's pay tribute to the Almighty Goddess with a traditional lamp lighting ceremony. I would like to request Dr. Anjali and Dr. Avni to kindly assist all our dignitaries on the dais for the traditional lamp lighting ceremony. Let's have a big round of applause. For filling this wonderful ambience in our function. How long is a second? How far is a meter? And how heavy is a kilogram? Everyone knows, at least roughly. But for a country aspiring large-scale industrialization, there is a need to move to precision than rough measurements. More than 75 years ago, a group of visionaries got together on the grounds of this very campus to lay the foundation stone to build an institute of eminence that would play a prominent role as a strategic enabler to bridge the gap between scientific and industrial organization and boost commerce. CSIR planned 11 national laboratories and National Physical Laboratory NPL was placed specifically in Delhi, the capital city. It has a peculiar role as the National Metrology Institute of the country. It was founded in the presence of some of the magnificent minds of the 20th century. Pandit Jawaharlal Nehru, Sir Charles Darwin, the director of NPL UK, Sir Harold Spencer Jones, Astronomer Royal, Professor Homi Jahangir Bhabha, Dr. S.S. Bhatnagar, Dr. S.P. Mukherjee, Sri C. Rajgopalachari, Dr. K.S. Krishnan, and Sardar Vallabhbhai Patel, the former Deputy Prime Minister of India. The core mandate assigned to CSIR NPL was to maintain the fundamental and derived measurement standards and undertake research to achieve high degree of accuracy in measurements through regular intercomparisons with other NMIs of the world. Today, CSIR NPL provides measurement traceability to nearly 4,000 agencies from government sector, PSUs, private industries, and SAARC countries. Today, CSIR NPL has the capability to measure with a few nanosecond accuracy, and accurate and precise measurements are the key to quality infrastructure development. With these words, I would like to invite our director, Professor Venugopal Achanta, to deliver the welcome address. Please, sir.
So, Honorable Minister, Dr. Jitendra Singh, Honorable DG, Dr. Shekhar Mande, Honorable Shri Ashok Kumar, Postmaster General Operations, Dr. C. Sharma, members of Research Council, Management Council of NPL, distinguished guests attending online and also here at NPL, and all my colleagues. This is a momentous occasion for all of us as we are celebrating the 75 years of foundation of one of the earliest laboratories of CSIR. In view of the prevailing COVID situation, we have curtailed the activities and also have taken precautions. To quote Honorable DG from the CSIR Foundation Day event, we have the same UVC disinfectant system fitted to the auditorium air conditioning system as that in the Parliament Central Hall. This technology is from CSIR CSO Laboratory, Chandigarh. We also have room UVC disinfectants, which are developed independently at CSIO and at NPL. So the effectiveness of these units against SARS-CoV-2 is tested by CSIR IMTech. And these are also tested and certified for the UV wavelength, intensity, and if there is any UV leakage or ozone generation at CSIR NPL. These products truly symbolize the collective strength of CSIR laboratories. So I'm happy to share that we have been using them effectively in the current events. CSIR NPL has the unenvious task of wearing 3 hats: to be the National Metrology Institute of India, being in the CSIR family to cater to industrial research. In addition, NPL is the physics laboratory in the CSIR system. National laboratories are defined to be the leaders in particular areas. For example, NCL, NML, which are part of CSIR family. In the early days, it was made sure that there is little overlap between the competence of different laboratories. For example, where I came from, Tata Institute of Fundamental Research, this is a national center for nuclear physics and mathematics. There's no duplicates in CSIR system. There is no equivalent mathematical institute or something in the CSIR system. Later on, we have multiple institutes under different departments, which were set up with overlapping expertise. For the first time in 75 years of independence, we have one minister in charge of almost all the science departments. We wish this augurs well for the Indian science under the able leadership of our Honorable Minister, Dr. Jitendra Singh. With the 3 hats which I mentioned, not just setting national metrology standards, NPL has actively contributed to addressing challenging problems for industry and strategic needs. one of the most famous examples which we hear about is the indelible ink. From indelible ink to carbon composite material for the nose cone of Agni missile, silver impregnated graphite for railway sensors to noise planning for metro rail projects, industrial process for synthetic diamond preparation to superconducting magnets, electrical energy meter calibration to the just unveiled LED calibration facility. NPL has been developing technologies over the last 75 years. In addition to these three hats, a fourth hat, which is additional work for our staff at NPL, is related to the improvement of the quality infrastructure within India. National Accreditation Board for Laboratories, NABL, and Central Electronics Laboratory, CEL, are offshoots of NPL. While most of us understand and appreciate the rigor that goes into the biology research, especially the amount of control experiments needed, the amount of data to be analyzed, the same appreciation is not generally offered to the metrology activities. To set up one calibration and measurement capability, a CMC, what we call, after the measurement is set up, analysis method put in place with the uncertainty budget of each equipment taken, every single step is put under rigorous scrutiny by international peers. The results are compared with that of other NMIs around the world before an intercomparison plot is made. All this takes anywhere between 2 to 5 years. For a scientist working in a research lab, the work is as much as 5 impact journal publications. Bharati Nirdeshak Dravya are certified reference materials with traceability. Rice BND, which will be released shortly, is developed by NPL by cultivating basmati rice over 3 years with infused heavy metals. This is the reference material needed for testing rice exports. The stability of any building depends on its foundation. All good NMIs in the world have strong basic research groups that support the future development of standards. Expertise in diverse fields is needed to set up a primary standard. Basic activity at CSR NPL should grow stronger. For this, we need to take up cutting-edge research and develop instruments and technologies. These should translate to products for scientific research. Challenges we face at NPL are related to staff strength, which decreased from 300 plus to about 400 now. Compare this again with TIFR. It started with a note from Dr. Homi Baba to Mr. Setna of Tata Trust, requesting for 1/3 of the annual budget of NPL to set up TIFR. From the second year onwards, TIFR got most of its funds from CSIR. Now, while TIFR has expanded its footprint all across India with various centers, NPL has shrunk in size, both in terms of funds as well as staff, compared to TIFR. We need to have a mechanism to hire students who are well-trained during their PhD at NPL. We are losing this manpower, well-trained manpower right now. As part of the CSR family, NPL has always addressed the challenging industrial and strategic needs of the nation. The compendium to be released shortly is a tribute to all the members of CSR NPL who addressed challenging problems in the last 75 years. With the past glory pushing us to set even higher standards and the government policies to be vocal for local, skill development, make in India, and finding solution to the local problems at the local level with global know-how, NPL as NMI, the National Metrology Institute of India, has to stand up as a leader and take the rest along by setting standards. In the next 25 years, to stand up to the ambitions of the nation as a world power with a strong economy that has opportunities for the world's youngest population, NPL's tasks are cut out in 3 fronts. Global recognition as an NMI with homegrown primary standards and measurement capabilities, which are supported by cutting-edge basic research. As a local hub to rope in Indian agencies and institute to develop BNDs, that is certified reference materials, and promotion of measurement standards and quality infrastructure within the country to support scientific and industrial growth. With this, I welcome you all to participate in the 3-day events to celebrate these 75 years of NPL. Welcome you all.
Thank you, sir, for the welcome address. Especially, I love the way he said that we need to focus on metrology and how NMIs are needed to given the right amount of importance and all the metrologists who are working in NPL. Last year, we began the 75th year celebrations of CSIR NPL, and today we are doing the Platinum Jubilee year celebration. In all these celebrations, the Director General of CSIR has been one of the most important personalities, and we really thank the DG of CSIR, Dr. Shekhar C. Mande, who is also the Secretary of DSIR, for making all these functions possible. Now, I would like to request DG sir to kindly deliver an address to the gathering.
Honorable Minister, Dr. Jitendra Singh Ji, Director NPL, Venugopal, Postmaster General Shri Ashok Kumar Ji, Dr. Sharma, all the dignitaries present in the audience, and people who have joined online. It's a great occasion for any institute to reach the milestone of 75 years. And if has traversed such a glorious path in these 75 years, it's even more important. I recall last year on this particular day, at this particular time, we were all of us in this audience, and we had the privilege of having the Honorable Prime Minister of India, Sri Narendra Modi Singh Ji, who addressed all of us in his capacity as CSI's President and as the Honorable Prime Minister of India. And at that time, the Honorable Prime Minister also recalled a number of things that NPL has done during 75 years, especially its role as the National Metrology Institute and how it has served the country well. Gopal told you a few examples. We are very proud of NPL, what it has done in these 75 years and contributed to the growth of the country. The formation of, for example, the Atomic Energy Commission, which happened very much on these grounds. Whether the rationalization of calendar system of India, where the Meghnad Saha committee came and CSIR piloted that through the help of NPL in 1956, till all the way where we even today preserve India's constitution in the Parliament Hall. NPL has played a very significant role in bringing the latest technologies, especially those under the physical sciences, to the country. And we saw a glimpse of that even today in measurement standards of luminosity or those of quantum clocks that the projects which are going on. All of them surely will make us proud in the coming years. I'm very pleased that NPL has done all these things in somewhat laid back or rather manner in which it has not been disseminated to the larger section of the society, the contributions of NPL. So many people probably may not be aware of that. And Honorable Minister has been guiding us all the time in this particular aspect. And he has also been saying, probably he will say today also, that during the educational tours of students to Delhi, NPL must become one of the destinations of the students. I would like to urge Director NPL to work with headquarters to make sure that we can do that and write letters to all the schools and colleges so that NPL becomes one of the destinations for the students and in a sense, disseminate what NPL has done over the years and what it is doing today to the students. I congratulate all the NPL family members once again for the 75-year journey and wish all of you very best for the coming many, many more years. Thank you very much.
Let's have a big round of applause for our Director General, sir, for his wonderful words. Next, we have a series of activities and facilities to be inaugurated by our Honorable Minister. First, we have a customized My Stamp and special cover. I would like to request Shri Ashok Kumar to kindly hand over the first album to the Honorable Minister to release the customized My Stamp and special cover. This is to commemorate 75 years of service of CSIR NPL dedicated in the service of nation. Let's have a big round of applause. As we can see, this is a My stamp. In this special album, we have the customized My stamp for CSIR NPL, and this is the special cover to commemorate 75 years completion of CSIR NPL. Thank you so much, sir. Our heartfelt appreciation to the Department of Post, Ministry of Communication from the whole family of CSIR NPL. Next, we have a compendium release on this historic occasion in the evolution of CSIR NPL as a world-class metrology and scientific institute. We feel proud to present 1947 to 2022, a compendium of scientific triumphs since our humble beginnings in 1947. I request the Honorable Minister to kindly release the compendium on this special occasion. Let's have a big round of applause, everyone. This compendium is a record of the initial struggle of the formative years, followed by decades of dedicated evolution and progress to coming of age at present. The CSIR NPL today has globally competitive calibration and measurement capabilities, along with innumerable products for societal benefits. I would now, next we'll have the release of Bharatiya Nirdeshak Dravya. So we have the BND release. So I would like to invite on stage Dr. Nahar Singh, Dr. Pallavi Kushwaha, and Mr. Vinay Jalan. BND is a certified reference material, a trademarked and registered by CSIR for self-reliance and to support the testing and calibration laboratories for quality assurance at par with the international standard. Recently, CSIR NPL, in collaboration with 12 RMPs, has developed more than 115 BNDs. Today, we are releasing 8 new BNDs. First is the high purity gold BND 4201A and gold alloy 916 BND 4202. Both BNDs are intended to be used as a gold reference standard for calibration of instruments such as XRF, method validation, and production of secondary reference standards. Let's have a big round of applause, everyone. I would like to thank the Honorable Minister for releasing the gold BND. Next, in the same category are 2 other BNDs, high purity silver BND 4101 and silver alloy 925 BND 4102. These BNDs are intended to be used as a silver reference standard for calibration of instruments such as XRF, method validation, and production of secondary reference standards. We can have the team Dr. VN Singh, Mr. Dinesh Singh, Dr. Vipin Jain, Dr. SP Singh, and Ishwar Jalan, Vinay Jalan, Paridhi, Om Prakash Gupta, Kamla Prasad Tripathi, and Buddhasen Patel. If anyone is here, you can stand in front of the dais to maintain physical distancing, and we can have a good group photograph. This is developed by Jalan Reference Material Producers, a unit of Jalan and Company, Delhi, India. So let's have a group photograph with the CSIR NPL team and the RMP team along with the honorable dignitaries on the dais. Have a big round of applause. Next, we have the second category is cement and cementous materials. We are releasing two BNDs, Portland Slag Cement BND 5053 and Blast Furnace Slag BND 5059. I would like to invite on stage Dr. Nahar Singh, Dr. V. Ezil Selvi, and Dr. B.N. Mahapatra. We can have the team members, Shri Amit Trivedi, Suresh Kumar Shaw, Shri V. Nagakumar, Shri Abhishek Agnihotri, Mr. Gaurav Bhatnagar, Mr. Suresh Wanguri, Dr. Varsha Liju, Dr. Swarupa Tripathi, Dr. Vipin Jain, Dr. SP Singh, to kindly stand in front of the dais so that we can have a very good group photograph to commemorate this event. Let's have a big round of applause, everyone. These are the Indian certified reference produced by RMP NCB Ballabgarh. These CRMs are intended to be used as a primary standard for calibration of instruments, validation of method for analysis of cement and cementous product, as well as the proficiency test for quality assurance. Thank you so much. Next, we'll be releasing the BND in chemicals category, BND 1031 Barium Standard Solution produced by Ashvi Technology. I would like to invite Dr. Nahar Singh, Dr. Swarupa Tripathi, and Dr. Neeraj Pandey on the stage. And the team members, Mr. Tushar Parekh, Mr. Priyesh Amin, Dr. Meenal Pandey, then from CSIR NPL, Dr. Swarupa Tripathi, Dr. Anuj Krishna, Dr. Jyoti Pokhriyal, Mrs. Dibya Dolrich Topo, Mr. Praveen Yadav, Chinki Kochar, and Lakhan Taneja. Kindly stand in front of the dais. This is intended to be used as a primary calibration standard for the quantitative determination of barium, calibration of instruments, and validation of method for the quantification and characterization of the measurement. Let's have a big round of applause, everyone, as we release this BND for barium standard solution. Thank you so much. And in the final category, we have a release under the food and beverages BND 3001 toxic elements in rice flour. I would like to invite on stage Dr. Nahar Singh, Dr. Swarupa Tripathi, and Dr. Anuj Krishna. And for the team, Dr. Jyoti Pokhriyal, Mrs. Dibya Dolrich Topo, Dr. Harish Chandra, Ms. Suresh Raina, Sunita Raina, Mr. Praveen Kumar Yadav, Lakhan Taneja, and Chinki Kochar. I would like to mention that this is an indigenously developed BND by CSIR NPL. It is intended to be used as a primary calibration standard for the quantitative determination of lead, cadmium, arsenic, and mercury. This BND is cultivated indigenously at CSIR NPL using basmati rice of Pusa 1121 and induced with toxic elements. Let's have a big round of applause, everyone. Thank you so much. Here we come to the end of the BND release program. Next, we have a launch of the responsive website of CSIR NPL. I would like to request to kindly bring a remote to the Honorable Minister so that we can remotely launch a new website of CSIR NPL. Have a big round of applause, everyone. The theme of the new NPL website being launched is to commemorate Azadi Ka Amrit Mahotsav, a Government of India initiative. The main aim of this website is to showcase and disseminate the details about metrology related activities of CSIR NPL in a fully responsive and more appealing design format. It will foster improved science communication with the stakeholders. Let's have a big round of applause. Next, we have the inauguration of a new calibration facility of infusion pump analyzer. Let's have a remote so that our Honorable Minister have a big round of applause, everyone. Biomedical metrology activity at CSIR NPL supports the healthcare sector, including hospitals, clinical laboratories, and calibration and testing laboratories in India by providing calibration services for medical devices. The CSIR NPL has developed a calibration facility for infusion pump analyzer for accurate measurement of parameters associated with an infusion pump to support the quality infrastructure in the healthcare sector. Thank you so much, sir. Next, we have the launch of the certification process for Indian-made low-volume PM 2.5 samplers. I would like to request the Honorable Minister to kindly inaugurate this with the remote. Have a big round of applause, everyone. The Ministry of Environment, Forest and Climate Change has designated the CSIR NPL as a verification and certification agency for emission and ambient air pollution monitoring equipment through a Gazette notification. CSIR NPL has developed a CSIR NPL India certificate scheme to provide certification of performance evaluation of air pollution monitoring equipment. Next, we have the launch of certification process for ambient ozone analyzer of Indian manufacturers. I would like to request the Honorable Minister to kindly inaugurate this with the remote. Have a big round of applause, everyone. We have established a testing and calibration facility for ambient ozone monitoring equipment through the Primary Standard Facility SRP 43. The testing facility will help to validate the equipment measurement capabilities and provide certification for its intended use. It will facilitate indigenous manufacturers to demonstrate the quality of their equipment and overcome trade barriers in a cost-effective way. Keeping in mind the current scenario of air pollution, this is a very important and indispensable facility for India. Next, we have, as I already mentioned, we are celebrating the Platinum Jubilee year. So we have various programs planned from 4th of January 2022 until 6th of January 2022. Keeping in view of that, we are inaugurating the Metrology Conclave 2022, which will be held in this auditorium this afternoon. We organized the Metrology Conclave on our Foundation Day, and this year it's quite special because it's Platinum Jubilee year. The theme for this year is recent trends in metrology. This will be an opportunity for stakeholders to brainstorm and explore the gaps in the existing national metrology scenario and recommend remedial steps to fill the identified gaps which would directly affect the country's economic growth. The invitees for the meeting would be from various NMIs across the globe, several thousand participants from CPCB, Legal Metrology Labs, NABL, ICAR, NCCBM, and various other academias, calibration and testing laboratories. This conclave would mainly focus on deliberations with delegates having diverse expertise, including policymakers, regulators, academicians, and scientists. Now, I would like to invite our Honorable Minister to officially inaugurate the Metrology Conclave 2022 and address the gathering. Please, sir.
I didn't intend to be that tall. Only the flower bed was very high. And certainly standing in this hall, nobody can afford to be taller than the founding fathers of this hall. So we have to be very humbly conscious of that fact. Thank you very much. Director General CSIR, Dr. Shekhar Mande, Director NPL, Professor Vinu Gopal, Mr. Ashok Kumar, Postmaster General of India, Dr. Sharma, senior members of the fraternity, faculty of the NPL, ladies and gentlemen. At the outset, it's my privilege to be here on this momentous occasion and also be a witness to a series of launchings and inaugurations, including the special commemorative stamp on the occasion of the Platinum Jubilee of NPL, the host of other launchings that you just now witnessed, and of course the Metrology Conclave, which is to follow this afternoon. I do feel very humble and small when I stand before you this morning, and I'm very deeply conscious of the fact that we are actually right now having a brush with the history. And we are having a brush with history for more reasons than one. Because we are standing at a place and a venue which is etched in the history of immediate pre-independence India and also immediate post-independence India. And therefore, maybe it was God's blessing and our destiny that we were to be here exactly 75 years after this place witnessed the gathering of a galaxy of great Indians, including Sardar Patel, Sama Prasad Mukherjee, Dr. Bhatnagar, and of course the then Prime Minister Jawaharlal Nehru. Also, I'm sure this day would remain memorable for the rest of our lives because this is an institution which is indeed a monumental illustration of India's incredible journey over the last 75 years. And it is also a demonstrative monument of India's capacity to rise to the top of the world on the basis of the strength of its scientific attributes and scientific talents. And that would also, if we think deeply, make us realize that we always had scientific potential in abundance right from beginning. And what was perhaps lacking was not enough of prioritization at the level of the policy planners, at the level of top hierarchy, at the level of the ruling dispensation. And therefore, without hesitation, I can claim that this moment of reckoning had to arrive at the time and the date that the Almighty had decided. And that date and time happened at around 6 o'clock in the evening on 26th of May, 2014, when Shri Narendra Modi took over as the Prime Minister of India. And Modi ji indeed came as a redemption for many of us at many levels. And as far as the scientific fraternity is concerned, it was a very fortunate coincidence that we have at the helm of affairs of this country a person who has a natural temper for science, a natural leaning for science. And that we saw very beautifully manifesting during the COVID times. And also, because this was the first time that we saw a budget hike for our scientific endeavors, and above all, the personal indulgence of the Prime Minister of the country. And as I was saying a few moments ago, COVID in fact came both as a blessing and a curse for us, because it demonstrated and proved to the world India's unrealized capacities, unrealized potentials, and its inherent resilience under Modi, which could turn an adversity into virtue. And when we celebrate the Platinum Jubilee of the National Physical Laboratory, I think what is not much discussed outside, not even the media, that all the science streams which are associated with this 2 or 3 ministries had substantially contributed in the war against COVID. Though they were not so much celebrated because these departments do not catch the public eye in the manner in which some of the other departments and the ministries catch. But it is a fact that the first DNA vaccine trials were done in the Department of Biotechnology, though the later part of it was taken up by others for obvious reasons. Even today, most of the Omicron assessment is being done by the same department. It was the same department. Today, you read in the newspapers that more than 80% or around so much number of cases are Omicron affected in Delhi. The newspapers might not have reported, but I might share with you that this finding happens to be from the Department of Biotechnology associated with this ministry. It was the CSIR, of which the NPL is also a part, which was actually conducting trials on remdesivir even before anybody had heard about corona or COVID. So what I'm trying to say is that we were already into it. We had not waited for COVID to happen. And when the COVID did happen, all these allied ministries and departments were prepared to accordingly orient themselves to face the challenge. Since I'm also dealing with atomic energy space, it is the atomic energy which, when India was actually faced with the shortfall of available number of PPE kits, and we had all the hospitals across the country clamoring for, asking for PPE kits for their health warriors, health workers, it was the Department of Atomic Energy which came out with a mechanism to facilitate reusable PPE kits by using radiation techniques. So what I'm trying to say is that in the kind of times that we live, our role has not only got extended, but it has actually become very critical. It may not be much talked about today, but it would be realized very soon. And those who understand are realizing it. I don't know how many of us have given a thought to the fact that ever since Shri Narendra Modi became the Prime Minister of India, virtually in every Independence Day address from the Red Fort, he makes one or the other important declaration of intent related to science, technology, innovation, and his address is heavily loaded, underlining science technology, which was not so in the earlier years. Many of us would have followed the prime ministerial addresses to the nation on the 15th of August. For example, in his very first address as the Prime Minister, he referred to Swachhata. Now, Swachhata seems to be a very innocuous concept, but it had deep scientific, clinical, medical connotations. And when he emphasized on building of toilets for girl children, there was a deep thought based on years and years of research, because non-availability of toilets is expected to enhance the risk of diseases among girl children, particularly the ascending urinary tract infections, to which the girl child is more prone compared to the male child. So these are the statistics that we had been portraying even in medical science for years together. But the policy planners thought of it when the Prime Minister took up the baton. Similarly, in another Independence Day address, he referred to digital health. And I'm sure in the times to come, we'll talk of doctor as a digital doctor. And when you go for a consultation, you will say, is he a doctor or a digital doctor? Because you would like to go in for the best, who may not be available in Delhi, but that will not be a barrier. Like I was saying other day in VHU, when we were small, the color films had just arrived, Eastman color. So we children didn't have much of a permission to go for a movie. So carefully we would ask each other, Rangeen film kaun si lagi? So that became an important criteria regardless of the content of the movie. So that's the, and it was Prime Minister who announced this. And he was always announcing these aspects even before they had actually touched the mind and the conscience of the nation. And the nation would then take a cue. Similarly, this year he spoke of hydrogen mission. And again, we are going to be having a role in that too, along with the Environment Ministry, as the science streams and science departments. And it's only after Prime Minister has announced that people have woken up to understand what's it all about. So what I'm trying to say is that we have a government which is supportive of all the initiatives that we undertake, and now it's up to us how far we are ready to go, how far we have the capacity to carry ourselves, because that is going to be a dynamic capacity growing from day to day. So how fast can we equip ourselves? But I am satisfied to see and notice in the last half an hour that all these launchings and inaugurations which have happened today are actually an extension of the same roadmap which Prime Minister Modi has unfolded for us. Whether it was the dedication of the LED photometry laboratory, because it was the Prime Minister in his early months, he was repeatedly emphasizing on the use of LED bulbs for reasons of cost effectiveness, for reasons of clean energy, etc. And we have today contributed to that mission, the facility to characterize the test LED-based lighting systems. Similarly, the school students' science exhibition, as was being referred by Dr. Mande, we went through and now he was saying that I might say again, though I don't know whether I would have said again, but now since he has said I might say again, so I'll have to say again. What I have been saying for over a decade now. And I think now we have a mandate to do so. We had been requesting the Education Ministry, the Tourism Ministry, that they should include these monuments of modern India in their itinerary for the educational tours. In fact, way back 10 years back, I had specifically represented with the name of the National Physical Laboratory. So I said, you have to get over those 200 years old list of Red Fort, Jantar Mantar, Qutub Minar. Because in any case, the children would see that otherwise also. But we have to tell them what they ought to see. And the exhibition which has been inaugurated this morning, I think would also become meaningful if it only reaches those for whom it is meant. Otherwise, we'll be seeing what we are seeing every day. So I think soon we'll devise some means. The Director General can even write to the counterparts in the Education Department Ministry, also in tourism, to encourage their students. We try to do that in the Pragati Maidan. We set up a separate pavilion for atomic energy, and we named it Hall of Nuclear Power. But in spite of our insistence, not many schools or their authorities encourage. However, over a period of time, at least on holidays, students on their own are coming there. But I think the location is different and this is a different place. So we would have to make an extra effort. And then I have to also congratulate the Department of Post for having commemorated this occasion, because in the kind of setup that we live in India, a commemorative stamp carries a huge symbolic recognition of the event or the occasion, which we have done today. And the launch of the websites and B&D, and of course, PM 2.5 samplers, all these are in keeping with the kind of progress that is, and we say it, expected of India in the years to come. Now the task and the challenge both for us would be how to move forward and how best to move forward. And that now, as was being mentioned, Azadi Ka Amrit Mahotsav, it's repeatedly the 75th year of India's independence, which coincides with the 75 years of Platinum Jubilee year of National Physical Laboratory, were being mentioned one after the other by each of those who spoke. I think now, having gone through it, the next task is what do we do in the next 25 years? And if we have to arrive at optimum results, I think we have to ask ourselves or pose before ourselves 2 or 3 questions or maybe obligations that we are expected to fulfill. A, how to integrate amongst ourselves. Because integration at a larger scale is no longer a choice or an option. It's virtually become a necessity. So we have to integrate among the science streams and also in the wider stream. Now all these releases that were done, whether it was a B&D, whether it was that Jalan coins, all those things can be put to the practical use or application only we have on board, of course, all the areas related to science, but in addition, the industry, the stakeholders, so that we are able to carry forward for the purpose all this has been done. And that would also pose the next question to us, how best to translate all these launchings to bring in ease of living for the common citizen. Now we've done a launching for air pollution. We are going to have a conclave on metrology. And at the same time, even a capital city like Delhi is most beset with the problem of pollution. The other day I went to Cochin and suddenly I realized the leaves of the trees were so green. I thought something had gone wrong with my eyesight or overnight it had improved. And then I realized, no, for months together we had not seen the greenery of the tree ahead. So how best to translate all these? That is the second question. And third, which is most important for all of us, how best to give esteem to the scientist so that he becomes a scientist by choice, not by process of rejection or elimination. कि और कुछ नहीं बन पाए तो scientist बन गए. So as long as that happens, we would not be able to put our heart and soul into this. If we are able to at least do that, I think we would be able to, because we have immense amount of scientific potential, but the esteem is lacking. and we are able to connect that, make it more attractive, more lucrative, more respectable, we would have the best of the brains coming to us. And in this year, we have laid down before ourselves some of the tasks related to the Amrit Mahotsav. I think this is an occasion to reiterate because we are celebrating 75 years. I have requested all the secretaries in the science ministries to identify 75 young scientists, young startups, and then link them with livelihood stakes. Because unless you have young scientists linked with or their stakes held on, hooked on to livelihood, you will not have sustainable startups. So we've been talking about startups for the last 5-6 years. I think now the time has come to talk about sustainable startups. Otherwise, you start up and then they start out because they go for something else. And I have also suggested that we should try to reach out to them rather than they reaching out to us, so that we could search the best talent, even if it is not realized by the individual concerned. We can manage. And we have also started a mentorship program so that the potential young scientists can be spared from the evil influences of the society around who drive him into Mukherjee Nagar coaching centers, so that they can show him where is NPL, what is there. For that, we need to have those who can actually also educate the parents. Similarly, 75 women scientists will try to identify, because we've already started a process of doing a retrospective study to make ourselves understand where have those women scientists gone who were trained by DST maybe 10 years back, 12 years back. Did they end up becoming civil servants? Did they end up becoming housewives? Or did they carry on with that pursuit? Because there's a whole lot of social pressures also around. If so, we'll have to reorient ourselves so that we could make, again, create sustainable women scientists. Now that we have in large numbers, the other day I put a question, I think they are now working on it. Why is it that in India today, even today, in class 12 and in graduation, you have such a huge number of women scientists, women science graduates, but the women scientists are not proportionally so, which means that they may be taking science streams looking for some other goal, not to become a scientist, but to have a good score. So we have to overcome these challenges. We actually want to translate this on the ground. And as I said, this is the best time happening for the scientific fraternity. The Honorable Prime Minister is very forthcoming and encouraging in whatever we do. As we have to, it's up to us to make the best use of it. Dr. Mande was referring that they gathered here last year this day on the 4th of January. I'm sure they have been gathering here on the same day for the last 75 years. And they'll keep doing so for the next 75 years also. But the most celebrated occasion would come 25 years later on 2047, when I'm not sure whether I and Mande would be here. But what we can do for our satisfaction is to groom those young scientists who would be there to celebrate the centenary of NPL, coinciding with the centenary of independent India. And then they would be able to tell their children or their juniors that part of my grooming happened in the hands of Dr. Mande and Professor Venugopal. So with that kind of enthusiasm and dream, ladies and gentlemen, let's move forward as best as we can. Thank you.
Last year, we had the President of CSIR, the Honorable Prime Minister of India, Shri Narendra Modi ji. And today, we have the Vice President of CSIR, the Honorable Minister. Thank you, sir, for such enthusiastic words. And it shows the real picture of science and technology and how we should take steps to move forward. As we go towards the end of the ceremony, we have a special memento, the special metrology clock. As we all know, CSIR NPL is the timekeeper of the nation, maintaining the Indian Standard Time with a few nanoseconds accuracy. So we are commemorating the Platinum Jubilee with a metrological clock. I would like to request the Honorable Director NPL to present this memento of special metrology clock to our Honorable Minister. I would like to request the Director NPL to present the memento to our Director General, Dr. Shekhar C. Mande. Now, I would like to request the Director NPL to present this special metrology clock to Sri Ashok Kumar from India Post. Thank you so much, sir. I would like to say it's not a simple clock, but a representation of the fundamental base SI units. This metrology clock is comprising of a proper ruler having 30 centimeter length at the base for measuring the length and the whole piece weighing close to 1 kilogram so that it can be treated as an artifact of mass. The dial of the clock shows all the 7 base SI units, and it also contains a picture of the universal solar system at 11 o'clock position and a picture of the sun and earth at 12 o'clock and 1 o'clock positions respectively. The logos of CSIR and NPL are also included in the dial at 10 o'clock and 2 o'clock positions, which is the primary responsibility for realizing the SI unit. The fundamental constants of nature from which all these base units are derived are shown as the pillars of measurement units and the traceability pyramid. The sun stands for the light radiation from which we derive the unit candela. The hour and the minute hands are indicated with thermometers representing the measure of temperature, Kelvin. Small windows are made for indicating the room temperature and the illuminance appropriately. The second hand of the clock has a horseshoe magnet, indicating a moving magnet in coil producing electric current in ampere. And the molecules at the center of the dial represent the mole. So, a single metrology clock is very special as we commemorate the Platinum Jubilee celebrations. Let's have a huge round of applause. Now, I would like to invite the chairman of the organizing committee and the chief scientist at CSIR NPL, Dr. Shimendra Sharma, to kindly address the gathering with a vote of thanks.
A warm and graceful good afternoon to our chief guest, Honorable Dr. Jitendra Singh Ji, Vice President of CSIR, Dr. Shekhar C. Mande, Director General of CSIR, Shri Ashok Kumar, Postmaster General, Operations, Delhi Postal Circle, Department of Post, Professor A.K. Grover, who is with us now, who is the Chairman of the NPLR's Research Council, Professor Venu Gopal Achanta, Director CSR NPL, distinguished guests present in the auditorium, and also who are now with us on virtual platform, my NPL colleagues and dear friends. It's my privilege to propose a vote of thanks. I, on behalf of the NPL, extend a hearty vote of thanks to our chief guest, Honorable Dr. Jitendra Singh Ji, who spared his valuable time from his busy schedule to grace today's function. Sir, your words and vision shared with us today will encourage us in our future endeavors, and we'll plan accordingly to fulfill your visions. I also want to thank our Director General, Dr. Mande, for providing guidance and full support. And I recall now that it was during one of his visits to NPL in the later half of the 2020, when the plans for celebration for Platinum Jubilee year of CSR NPL started taking shape under his guidance. As a result of this, we have had a series of events started from 4th January 2021 to now. And thank you, sir, for your visionary leadership. We are grateful to India's Post for facilitating the unveiling of customized My Stamp and first day cover. On this momentous occasion, the presence of Shri Ashok Kumar, Postmaster General Operations, Delhi Postal Circle, Department of Post, and his team on this occasion is highly appreciated. I want to put on record our gratitude to Professor A.K. Grover, the chairman of the National Physical Laboratories Research Council, whose vision and support provide us the strength to accomplish tasks at hand. Today, we have had with us Professor Krishnalal, our former director. And we also have, we are grateful to our other past directors also, whose visionary leadership has actually taken NPL to the state where we are today, sir. Thank you very much for your guidance over the period of time. During this event, we have participation from our sister CSR laboratories, industry members and school children who are participating in various events like CSR Technology Demonstration Pavilion, MSME Meet, and Student Size Exhibition. I'm thankful to all of them for their contribution in adding immense value to our celebrations. The expeditious support received from the CSR headquarters at various times has contributed very significantly for the successful organization of this event, and we are very grateful to the CSR headquarters for this. I also want to thank our Director General, Dr. Finally, I would like to thank Professor Venugopalajanta, the Director of CSR NPL, for steering the organization of this event, and all the members of the organizing committee of CSR NPL, comprising of persons from scientific, technical, administration, finance and accounts, stores, purchase, PME, CFCT, BDG, works and services, air conditioning, HLS, horticulture, and other sections for their dedicated and untiring efforts in making this event successful. Thanks to all of you and have a great day ahead. Thank you very much.
Thank you so much, sir, for delivering the vote of thanks. Now, I would like to mention again that we are celebrating the Platinum Jubilee year of CSIR NPL that will be spanning from January 4th until January 6th. I request you all to visit the programs and actively participate in Metrology Conclave, the science exhibition for school students, the CSIR Technology Demonstration Pavilion, the MSME Meet, and the stakeholder meeting on certification of air pollution monitoring equipments. And while doing so, kindly maintain physical distancing and wear your masks properly. And I would like to mention again that the auditorium is thoroughly sanitized with UVC. Now let's all stand up for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Now we all break for lunch. I request all the dignitaries to join us for lunch at Dr. A.R. Verma lawn, and all my colleagues of NPL kindly collect the lunch boxes from the respective offices. And let's all meet here again at 2 p.m. sharp for the technical session of the Metrology Conclave. Thank you so much. I would like to remind again that we'll be beginning the Metrology Conclave 2022. Kindly assemble sharp at 2 p.m. as various participants from the NMIs across the globe will be joining us. Thank you. Good afternoon, everyone. Thank you so much for joining us back after lunch. Now we will begin the Metrology Conclave 2022. We have the talks from various professors from NMIs throughout the world. The first session will be chaired by Dr. V.M. Tiwari, who is the Director of CSIR NGRI, Hyderabad. Before I hand over the session to Dr. Tiwari, I would like to say a few words about him. He obtained his postgraduate degree in geophysics from the Banaras Hindu University, Varanasi. He took up a scientific career at CSIR National Geophysical Research Institute, CSIR NGRI, after receiving a PhD in geophysics from NGRI BHU. Dr. Tiwari's research interest primarily focuses on deciphering subsurface mass distribution and mass transport relevant to a wide range of scientific and societal applications, studying the Indian lithosphere, variation in water storage over Indian subcontinent, and mapping of the sub-basaltic sediments. He is a recipient of the National Merit Scholarship, ONGC AEG Best Thesis Award, Young Scientist Awards from INSA, CSIR, UP Science and Technology, Krishnan Gold Medal by IGU, and various others. He is also the member of several national and international committees. With these words, I think we are really grateful that Dr. V.M. Tiwari is going to chair the first session of our Metrology Conclave 2022. Now I would like to hand over the session to Dr. V.M. Tiwari and invite him on the dais. I really apologize that we are running a little bit behind our schedule. Kindly, this was because our first function of the inaugural ceremony ran a little bit late. I apologize to everyone on behalf of CSIR NPL family. I would like to request Dr. Richard Davis, kindly switch on your video. Okay, thank you, sir. I would like to request Dr. Anjali to kindly felicitate our session chair with a floral bouquet. Let's have a big round of applause. Thank you. Yes, sir. So we have actually 3 speakers. We can start with Dr. Richard Davis. I'll give you a mic.
Yeah, where is camera?
Camera is over there.
Very good afternoon and good morning to the speakers. We have three very distinguished speakers in the first session, and three of them are going to speak on three very different issues of metrology. Let us start with the first talk by Dr. Richard Davis, who works at NIST. He started his career in metrology as National Research Council postdoctoral associate at National Bureau of Standards, USA in 1974. He then became the member of the technical staff concentrating on mass metrology. In 1990, he joined the mass department of the International Bureau of Weights and Measures, BIPM. We all know very well. During 1993 to 2010, he headed the BIPM mass department. Upon superannuation from BIPM in 2010, he was accorded the status of honorary principal research physicist, and from 2010 to 2019, he became the consultant to the BIPM director until the major revision of the international system of units came into force on 20th May 2019. He authored large number of the scientific papers on metrology and the fundamental constants. He is also bestowed with Fellowship of American Physical Society in 1992. With this brief introduction, may I request Dr. Richard Davis to kindly start his presentation. We have 30 minutes for each presenter, and I would greatly appreciate that if we try to be in time. Dr. Davis, are you able to listen? Could you unmute your mic?
Okay, I think, can you hear me now?
Yeah, thank you. Yes.
Okay.
Very.
So I will start and I will try to keep the time and I first thank the organizers for inviting me to give this talk. It's on my favorite subject. So it's a redefinition of the kilogram, new challenges and opportunities, and I will get right to it. But first, before getting to the new stuff, I want to point out that measuring mass is an ancient activity. It's as old as civilization. So 4,000 years ago, there are these artifacts that remain, these blocks, small blocks of stone that were used by the Harappan civilization. And this was a civilization that is was centered in actually there was a large city in Gujarat, which was just and Dolavira, which is just become a UNESCO World Heritage Site. So it's appropriate to mention it, and I would say it's also a that's topic of current study. So there's even a recent paper from 2021, and these are two. Here we have two photographs in color of these stones that are mass standards, and these actually came from Dolivara. So, so now we get on to more recent things. I'll start with the three definitions of the unit of mass called the kilogram. So the first definition, just to recall what you probably know already, at least vaguely, dates from the time of the French Revolution and the First Republic of France. And it was created in 1799, and sanctioned in 1799 by the government, and it's made out of platinum sponge. So it's appropriate for your platinum celebration here. And in order to be less arbitrary, they decided to make the mass of this object equal the mass of 1 liter of water at specified conditions. So, so that was a kilogram, and it was kept in the archives of France. It was a French kilogram, but they invited other countries to follow suit. And in fact, by 1889, on the next picture, this is an international kilogram, the international prototype of the kilogram, called IPK these days for short. And this was the second definition, but it was really very close to the first definition, because this object is under 2 glass bells, and this object was made to have the same mass as this object. So it's very similar to the same definition. Actually, it was compared with this object in the 1880s. And so it had the mass of this object as it was in 1880. And we don't know what, of course, that's a problem with an artifact. You don't know if it's really the same mass as it had in 1799, but nobody can tell. So then the things stayed the same for many years. 2018, there it is in a more modern safe, and it's at the International Bureau of Weights and Measures, where I spent most of my career. And there are 6 official copies. Okay. And this is a very simple definition. It says whatever the mass of this object, the mass of this international prototype of the kilogram is exactly 1 kilogram. Couldn't be simpler. So now we come to the present definition, which took effect on May 20th, 2019. It's the third definition, and it's quite different. It says the value of the Planck constant, which is always represented by the letter H, is exactly this number. And its unit is kilogram meters squared per second. And if it's defined exactly, that defines the kilogram. Why? Because the meter was defined in 1983, and it still has that definition. The second was defined in 1967. It still has that definition, although perhaps it will change, as we'll find out from our next speaker. But so it's quite different. I mean, it's totally abstract. You don't see a picture of the Planck constant. You don't see a mass standard here, but it defines the kilogram, which is the unit of mass. So I will be talking about how this happens. And there are many preparations for such a big change. And one of the frequently asked questions is, what is a Planck constant? Most people don't know and don't have any reason to know. And so that and many other challenges face people. And so the first thing you have to do is have a value for the Planck constant, an experimental value, which it's always been found experimentally. You need an experimental value that has an accuracy which is comparable to the accuracy with which you can realize the previous definition of the kilogram based on the mass of the international prototype. And in fact, in order to measure the Planck constant, you need to be traceable to the international prototype because of the unit of the Planck constant. It's in terms of the kilogram. So if you can measure the Planck constant, then you can realize a new definition. So that is the basic way, at least. And then there may be other ways to realize the new definition, but at least you have that one. So if you see, so this was a paper that was published in 2017 or at least accepted for publication. And this was in preparation for the change in the units. So what you have is this is CODATA, which is an international committee that recommends the values of fundamental constants. And they examined all the data and they calculated what would become the exact value of the Planck constant and 3 other constants that were in the revised International System of Units, which took effect in May of 2019. And it says at the bottom of the abstract, these values are recommended to the 20th General Conference on Weights and Measures to form the foundation of the revised international system. So, so this is how it happens. This is how operationally you have to have approval from an international conference of weights and measures, and whose members are usually referred to as members of the meter convention, and each member gets a vote on important issues. And of course, India is a member, so India had a vote in this, and the vote was unanimous to accept these values to form the basis of the new International System of Units. So this is a remarkable achievement to get an international body of almost 100 or so member states to agree unanimously, but it happened. So it, and on here, there's a little inset of some of the data that the CODATA considered for recommending the value that you saw previously of the exact value for the Planck constant. Now I'll talk about that later. It's kind of a small picture to talk about here. And here I'll just say some more about why fixing the value of the Planck constant defines the kilogram and what that implication is. So at the top here, we have 2 equations. The first one, I think everybody knows, E equals mc squared, attributed to Einstein, this fellow over here. And we're so familiar with this, I mean, that we accept this. We know that mass can be converted to energy, and energy can be converted to mass, and the conversion factor is the speed of light squared. It looks simple. It's not simple. It's not easy to derive, but we accept it. And the second equation we need is another energy equation, and that says the energy of a photon is equal to the Planck constant times the frequency of the photon. So in this case, what it says is the frequency is low, like the frequency of red light has a lower energy than photons than the frequency of blue light. It's a higher energy. So, and it's true not just of visible light, but it's true all throughout the electromagnetic spectrum. So it's true for the photons of microwaves. It's true for the photons of X-rays, and all the way up and down the spectrum. So now I scoot over to this picture, which is the revised SI, and here's the kilogram, and here's the Planck constant, and here's the speed of light, because I mentioned in the previous slide, you need the speed of light, and I mentioned on the previous slide, you need, I said you need the definition of the meter, which depends on the speed of light, and you need the definition of the second, which depends on a fixed value for the frequency of the atomic clock, the cesium atomic clock. And so the frequency of the atomic clock has a fixed value, and it's a frequency, so you can plug it into this equation if you want. And so now this is a fixed energy, because the Planck constant has a fixed value. This frequency is fixed, has a fixed value to define the second. So this energy in the International System of Units has no uncertainty. So this defines the joule in the International System. And then you can combine these two equations. By the way, there's Planck. He is credited with the Planck constant, and usually with the Boltzmann constant, but I won't get into that. And so you combine those two equations and you get this one, and you get mass. A mass is equal, there is a mass that is exactly equal to the Planck constant times the clock frequency divided by the speed of light squared. And so that has a fixed value. You can't measure that. Its value is fixed in the International System of Units. So, but is that a kilogram? Well, no, it's actually 10 to the minus 40 kilograms. It's an exact value, but it's 40 orders of magnitude shy of a kilogram. And you're trying to replace a definition that is based on an object whose mass is by definition exactly 1 kilogram. So there's a 40 order of magnitude mismatch. So this is not the way to look at how to, this equation is not the equation you use to define the well, you use it to define the kilogram, but not to realize the kilogram. You have to find a clever way to realize the kilogram based on this definition. You can't define the kilogram in any other way than related to this, because otherwise you would have a system that was overdefined. Okay, so we come to some challenges. We've already seen some. The new abstract definition of the kilogram is a radical conceptual change. And I mean, for 4,000 years, we've been thinking of mass standard as an object that you pick up and you put on a balance. And now we have a definition where you don't have that anymore. But and it's a huge conceptual change, and you have to ensure that the change is invisible to the public. You know, and they have to be assured that a kilogram is still a kilogram despite this new definition. But it has to be carefully explained to interested users, because the kilogram is for everybody and users want to know what it is. So, so these are challenges. And now the definition has the advantage that it no longer depends on the mass of the international prototype, which is usually locked away in a safe at the BIPM and used rarely, and exploit the fact that the Planck constant is not the property of an arbitrary object. It actually makes more sense to measure the mass of the international prototype, which is just an artifact, in terms of the Planck constant, which is a fundamental constant of nature, rather than the reverse. And as we saw, the Planck constant is a fundamental constant of quantum physics. We saw how photon energy depends on the Planck constant. Many other things depend on the Planck constant. So we should take full advantage of this in metrology. So now I get back to this graph I didn't show before in detail. These are the data that were available to the CODATA, when they were recommending their value to the General Conference on Weights and Measures. So the data are of two types, as it says. One is XRCD, which stands for X-ray crystal density. The other is KB, which stands for Kibble balance, watt balance. And these are very different types of experiments. And while they're complicated and hard to explain in the short time I have, I can at least show you that they're very different. But getting back to CODATA, they had these data points and the uncertainties that the research groups assigned to them. And some are large uncertainties, some are smaller uncertainties. So CODATA did a weighted least squares. This is what they do all the time with data. So and they came out with the weighted mean of all of these measurements here. This was the value recommended to the General Conference. And that was the value that became fixed. So no uncertainty. That's the definition. So definitions don't have any uncertainty. So, so what happened to this uncertainty? It became zero when the value of the prototype of the Planck constant was fixed, but it's had to go somewhere, and we'll get to that briefly later. But let me just say about these two different kinds of experiments. The Kibble balance, sometimes called the watt balance, it realizes the kilogram by balancing electrical power with mechanical power. And they're both of these. Power is measured, doesn't matter what kind of power in the International System of Units, they're both measured in the same unit called the watt. So and if you measure the electrical power in terms of quantum electrical standards, which exist, and they have the Planck constant in their description, so you can, that's how the Planck constant comes into this. And it's, there are similar, more recently, there's work being done on the Joule balance, which is also an electromagnetic realization of the kilogram. And so all of these things have basically the same DNA. No matter how you do it, they're basically the same animal. And this one, X-ray crystal density, is very different. You realize the kilogram by counting the number of silicon atoms in a crystal that has a mass of approximately 1 kilogram. You count the, so it's a counting experiment. And at the end of the experiment, you have a number. Now, a number isn't a kilogram, but that number is the number of silicon atoms it takes to make up the mass of the crystal. And what you now need is the atomic mass of the silicon crystal, the mass of one atom, which is a constant of nature, and you have to know it with respect to the Planck constant. But this is known, and it's not going to change, because although the crystal could change, you can make a new crystal and it will have a different number of atoms. But an atom of silicon, its relation to the Planck constant is not going to change, and it's already extremely well known. So that it's actually the uncertainty of this step is already included in these uncertainty bars, where this extra uncertainty is completely invisible. You don't see it. It's so small it doesn't even appear as a lengthening of these uncertainty bars. So these are two extremely different types of measurements. This one uses a balance. This one measures the mass of a crystal without a balance. So, and they both give you the same Planck constant, which is pretty amazing. And so it's one thing to say they're different, and it's one thing to look at the equipment. So basically, this is the equipment at the BIPM back in 2019. It's quite different now, but It does, but basically this is your typical kibble balance, and there's a schematic. You see it has a weighing pan, it has a magnetic circuit, et cetera, et cetera. You measure electrical things in terms of quantum mechanical values. And here's the silicon one. And the silicon one is a complicated experiment, but you first have to be able to create a single crystal of pure silicon, preferably silicon 28, enriched in the isotope silicon 28. If you can't do that, you can't do the experiment, but you can do that. And so these are pools of pure silicon, single crystal. It's single crystal, so the crystals are in an array that, you know, and the array goes unbroken from the bottom to the top, from the side to the side. And in fact, this is how you measure you can't count the atoms. There are uncountably large number of atoms in a crystal, of macroscopic crystal. But you use a trick because if they're in a perfect crystal, you can use X-ray techniques to infer the number of atoms in the crystal. So you can make these single crystals, but the shape, you need to also have a shape you can deal with. So you have to machine them. This was all done at the PTB and in Germany. And so you start by chopping up, getting 2 kilogram crystals out of each of these, and then you gradually machine them and polish them until you get a usable shape, which is a sphere. And then you measure the volume of the sphere, which you need. And this is just a part of it, but just to show the difference in techniques. And the fact that you get the same Planck constant is reassuring. So there were some steps to be taken after the definition of the kilogram took effect. Some practical steps. And so there were we're in the middle of 4 phases of easing into this new definition in a practical sense. Phase 0, which is not really a phase, it says that the traceability to the international prototype, which is previous definition of the kilogram, is still in effect until 20 May 2019, when the new definition of the kilogram takes effect. In other words, don't use the new definition until 20 May 2019. Don't jump the gun. So the General Conference was quite explicit on this. So phase 1 begins on 20 May 2019. And then you say, well, what's our best realization of the new definition of the kilogram? Well, the best realization is the mass of the international prototype, because it was used to measure the Planck constant, the value of the Planck constant. So the mass of the international prototype is still 1 kilogram. It didn't change at midnight. On May 20th. So it's still 1 kilogram, but it's not exactly 1 kilogram. Remember, I said that uncertainty of 10 micrograms in the graph had to go somewhere, and this is where it goes. It goes to the mass of the international prototype. It's now, it's still a kilogram, but with an uncertainty of 10 micrograms for a while. It's an artifact that can change its mass, but for a year or 2 or 3, that will work. And this was going to last until the Consultative Committee for Mass approved what they call the consensus value resulting from the first key comparison of realization experiments. So the consensus value is basically the weighted mean we saw in the previous graph. It's like a weighted mean, but it has a different purpose, so it has a different name, and you can read all about it in the Metrology article, short Metrology article from last year. I have to remember to say last year. Okay, that's done. And then phase two, you disseminate from the consensus value until the consultative committee decides that the dissemination from the consensus value is no longer necessary. The people who can disseminate from the consensus value are the laboratories that participated in the calculation of the consensus value. So not just anybody, but these labs can do it. Until the CCM, Consultative Committee for Mass, decides that dissemination from the consensus value is no longer necessary. How are they going to decide? Well, they'll know it when they see it. These are all experts in mass metrology. So far they haven't seen it. And phase three is the final phase, dissemination from individual realizations. That's what everybody is aiming for, that all laboratories that have their realization of the kilogram based on the definition of the from a fixed value of the Planck constant, agree within their uncertainties, and therefore they can disseminate their value, very much like in every other field of international metrology. So that's the goal. So then I'll end with some consequences of the kilogram beginning to take hold, and not only in mass metrology. So there are but in mass metrology, you can imagine shorter calibration chains for small mass pieces, much less than 1 kilogram, say a milligram, less than a milligram. You could make a Kibble balance, maybe based on electrostatic energy, and you don't have to start at a kilogram and work down to a milligram or below. You can start anywhere along the scale because the Planck constant's everywhere. So, that's an active area of research. Quantum electrical standards are already in use. For example, resistance standards are based on exact values of the Planck constant and the elementary charge, which is also now has a fixed value. And from those two things, you can make something called the von Klitzing constant, which is the quantum of electrical resistance. And it's not 40 orders of magnitude different from anything we use. It's actually it's 25.8 kilo ohms. So it's quite useful. It's in use. And the big thing now is that it was so accurate that in the recent past, the mass metrologists had to use conventional values for the Planck constant and the for the Planck constant and the electrical charge and elementary charge, and these were close to the SI values, but not exactly the SI values. Now they're firmly in the SI system of units. There's work towards a quantum Pascal because quantum, Pascal is the unit of pressure. And we usually think of pressure as force per unit area. But if you just, that force per unit area is the same as energy per unit volume. And we know that energy can be related to a frequency of a photon. So there's a way of doing it. And this is very active. This is linked to work being done in Europe. So there's possibility for a quantum candela, and that's very well documented. And they've been thinking about a quantum candela since 2010. The candela is a unit of photometry. So it's another thing that's not very closely related to the kilogram, but it is related in a way. And so there are many more, but my time is out, and I knew it would be out, so I don't have any more than these, but it gives you some examples of where the world is heading. And so with that, I will end on time and thank you for your attention.
Ricard, thank you very much for your illuminating talk, right from bringing the information how the humans started understanding the standards, particularly mass standards, 4,000 years ago, and what are the new opportunities for NMIs going through the definitions and the challenges, the new possibilities by which we can improve. So with such a wonderful talk, I think we will move ahead to the next talk, and we would like to thank Professor Ricard Davis for his illuminating and interesting presentation. Thank you very much. Merci beaucoup, Ricard. Thank you. So next presentation, today's invited speaker is Dr. Gerard Petit, who is graduated from École Polytechnique, France, one of the very prestigious engineering college in France in 1979. He obtained his PhD in astronomy from Paris Observatory in 1994. After working in the field of geodesy, he joined in the International Bureau of Weights and Measures, BIPM, in 1990, where he now is a physical research physicist with the time department. So the previous talk, we were illuminated, told about the mass. Now we will having opportunity to listen one of the very eminent person whose research interest concern all aspects of the elaboration and usage of the time scales, especially time and frequency transfer techniques using GNSS, relativistic treatment for the time and frequency applications, and the use of the frequency standard in generating International Atomic Time, TAI. You all are very much aware the way the GNSS technologies are improving, and the astronomical observations combining with GNSS observations pose a new challenges in realizing to understand several possibilities which not only defines the standard but also having these observations for the planetary motions. Gerard received his very prestigious award from the European Frequency and Time Award in 2010. With this brief introduction, I have really a great pleasure inviting Dr. Gerard Petit to deliver the second lecture in this session. Gerard, it's over to you.
Hello, can you hear me?
Thank you.
So I will share the screen. Thank you for the introduction, and thank you for the opportunity to present this talk on time metrology and the redefinition of the second with some present and future challenges. I have to acknowledge material provided by Patricia Tavella, the head of the time department of the IPM, and Noel Dimarc, the chair of the consultative committee for time and frequency. I will have three sections. I will, of course, talk of the redefinition, and I will briefly remind the reference timescale UTC and TAI that the BIPM is generating, and the implication of the redefinition for UTC. In 2020, the consultative committee for time and frequency started a new task force to review the definition of the second. You know that since 1967, the second is defined by the duration of a certain number of periods of a certain transition of cesium. And this task force is going to review a new definition. It comprises several tens of specialists in the time and frequency community to review all aspects. First, the needs. Second, the technical method to redefine the second. And finally, the links to the time and frequency dissemination and time scales. The need for redefinition stems from this quite well-known plot, which shows the accuracy of the realization of the decades for the microwave standard, which follows the definition of the second, which is given by cesium, so in black. So in the last 25 years, this has been provided by so-called atomic cesium fountains, which now have relative frequency accuracy at very close to 1×10⁻16 in relative frequency, so something about 2×10⁻16 for the best devices. But the optical standards in the last 20 years, and especially since the introduction of the frequency comb about 20 years ago, that links easily the optical frequency domain to the microwave frequency domain, they have had tremendous improvements, and in a few years they have surpassed in accuracy the cesium fountains. And now the best optical standards have an uncertainty budget, which is at the 1×10⁻18 level, which is about 2 orders of magnitude better than cesium fountain. So that's the reason why it's time to change the definition. The task force that has been set by the CCTF has started working and defined a quite large number of criteria to be achieved before changing the redefinition. Actually, there are some mandatory criteria to be achieved and some other conditions that may be still in progress when the definition is changed. And we're not going into any detail. Of course, these criteria relate to verifying that the accuracy budget are really fulfilled, and that when the new definition comes into force, the new standards will contribute to UTC and TI and will be available to users. So, all these aspects must be checked before a new definition takes place. And there is this kind of advancement sheet which relates for all the criteria a kind of index of advancement. And you can see that as of the middle of last year, it's in various stages, and actually it's a field that goes quite fast. For example, the regular contribution of optical frequency standard to TAI was quite low in the mid of last year, but in the second semester of last year, there has been a quite good number of new contributions to TAI from the optical standard. So this now has moved a bit towards the right. So this will be reviewed every year by the Consultative Committee for Time and Frequency. The options for a new definition, there are 3 options have been considered. One is just to replace current definition of the second, which is based on one transition linked to the cesium atom, by a new reference transition, of course, in the optical frequency domain. The second option is a more ambitious definition where it would be based on an ensemble of reference frequencies, optical or maybe not optical, but at least an ensemble, and use a kind of weighted geometric mean of the ensemble. So I have, of course, no time to get into any details, but that's the second option which is being envisioned. The third option, which is about equivalent to what Richard Davis showed us for the kilogram, fixing the value of another fundamental constant is not possible for the, because at the theoretical prediction of the standard model of particle physics is not sufficient in accuracy. They would be 10 to the minus 12 at best, and it's already 4 orders of magnitude larger than the present definition. So it's not a practical way to go for this redefinition. In terms of schedule, given that the General Conference of Weight and Measure is every 4 years, and starting this year, well, the standard schedule envisioned by the CCTF right now is to aim at 2030, but of course it means that some milestones have to be reached for this coming CGPN in 2022, and also for the next one in 2026. The CCTF should be able to show in 2026 that it will be ready for redefinition before the next CGPM. So in case it's possible that an alternative schedule is chosen in the end, but this is still the way to go. Now, coming to the time scale of the BIPM, UTC, and TAI. This is the BIPM, and the snow, not so often happening. So just to remind you, what is the UTC, Coordinated Universal Time, and the TAI is the International Atomic Time, which is designed and generated by the BIPM. The BIPM has the responsibility for this since 1988, and on this plot you can see the number of participating laboratories to UTC in the last decade, since the early 70s, when the time scales were first defined, to now. So we are now 85 participating laboratories, and since the BIPM took responsibility, it issued the circular T for disseminating the results of UTC minus the realization of UTC by the participating laboratory. And this is a copy of circular T1 of January 1988. And you can see that NPLI of India has been a participating laboratory since the beginning of the BIPM participation to UTC, and participation has been continuous since that time. can also be seen that in the last 3 decades, performance of the time scales have been following the performance of the atomic clocks, and standards have been improved by 3 orders of magnitude from the 10-13 uncertainty level in the 1990s to 10-16 now. And just to show you the diversity and the number of participating laboratories to UTC, this is really a worldwide endeavor with participating laboratories in all continents, a bit more in Europe because for historical reasons and because there are also more larger number of countries in Europe. Just a words on the technical construction of the International Atomic Time TI, which is a 2-step process. Let's say the first step is a kind of weighted ensemble of hundreds of atomic clocks operated in all the laboratories. This step provides a stable intermediate timescale, which is named EAL, stable but not accurate, not necessarily accurate, not corresponding to the definition of the second. The accuracy is provided by a second step in which we use about 10 primary and also some secondary frequency standards which aim at realizing the SI second and steer the intermediate timescale to produce TAI, which is stable and accurate at the 10-16 level. When UTC is just the same as TI plus the leap seconds that you know of, so that UTC keeps more or less in sync with the rotation of the Earth. But that's another topic not to be discussed here. Just to show you some, to have a physical view of the devices, these are the commercial atomic clocks which provide stability to TI and UTC, which are present in all time laboratories. The main types are hydrogen maser and commercial cesium clocks, which have very good long-term stability. And the primary frequency standards, which provide accuracy to TI and UTC, and which are laboratory devices and not commercial devices. So here's a photograph of a cesium fountain. This one is in Switzerland. And now we have about 10 laboratories operating this kind of primary frequency standards. And best accuracy is about 2×10⁻16, as I said previously. This is the case for the CERT in Paris, the NPL in UK, PTB in Germany, INRIM in Italy, NIM in China, METAS in Switzerland, and a few others which are not shown here, which contribute regularly to the accuracy of TAI. But in addition, we also have a few numbers of the secondary frequency standards, which are the new optical frequency standards, which have a much better uncertainty budget than the cesium fountains. And those are mostly of the type of lattice clock, either based on strontium atom or on ytterbium atom. Presently, we have 7 such contributing standards, which are either strontium or ytterbium lattice clocks, which are operated in 6 different laboratories. If we look at this plot, which is available on the BIPM, time department database, at this address, you can see over the years, in the last 2 decades, the number of contributions, mostly by cesium fountains. As you can see, it has started in this century, around 2000, and much increased over the years. And the optical standards here started real contribution actually in 2017, but have been much increased in the recent year. And we can see that the NPLI cesium fountain had some contribution a few years ago that were taken into account to provide TI accuracy. So there is a large increase both in cesium fountain, but also in now, fortunately, in the reports of optical lattice clocks. And the result of this is that the accuracy of TI is now very close to 1-16, and it cannot go much below because of the limitation of the present definition of the second. But the input of the optical frequency standard, it's increasing, but it's still limited. So we need to have more contribution by optical frequency standard before the new definition takes place. Otherwise, even if we change the definition, we will lose in accuracy for TI. So this is one of the first challenges of the next years, is to have more and more continuous contribution of optical standards. Another implication for UTC is that the clocks which are operated in remote laboratories have to be compared, and they have to be compared to an uncertainty level which is at least as good as the performance of the clocks. And presently, the main technique that is used to compare remote clocks is using global navigation satellite systems, where we have one GNSS satellite which sends signals with timestamps which are received at 2 different laboratories, A and B. And by later processing together the data of laboratory A and laboratory B, we can get the difference between the clock in A and the clock in B. That's the main technique that we are using now to compare remote clocks, GNSS. We have another technique, which is also two-way satellite time and frequency transfer, which use this time transponder on board geostationary satellite so that the two stations simultaneously transmit data and receive data, so that cancels some of the uncertainty in the transmission time between the ground and the satellite. So these are the main techniques which are used now to generate UTC and compare the clocks which are used for UTC. And both techniques have performance which is somewhat limited to the level of 1×10⁻⁻16. Of course, there are some progress to be expected from these techniques. I will briefly mention this, but something has to be done to find a new technique to really reach the kind of transfer uncertainty consistent with the optical frequency standard. So one option is, of course, using fiber links, which have been in operation for quite some years now, and they clearly have the potential to provide the necessary uncertainty to compare optical frequency standard. It has been shown that the frequency can be compared to the level of 10⁻19, which is even better than the best frequency standard, even below 1 day in a few hours. But so it's a technique that is becoming mature, but the problem is there are two problems. One is that you have to build the fiber networks and also all that is needed to transmit the frequency signal over the networks. And the second one is that so far it's quite difficult to cross the oceans. So the extension of such networks is limited at this moment to about 1,000 to 2,000 kilometers and is anyway limited to continental areas. So there is a possibility to have other space-based techniques using microwave signals. And there is one experiment which is going to flight on board the International Space Station probably in the middle of this decade. That's the ACES atomic clock and soul in space experiment, which has cesium clock and new microwave link, which is not only two-way, but let's say 2+1 way, which has several signals transmitting from the ground station to the space station, and provides typically something like 10 to minus 17 at one day. So it's one path toward future technique which could allow to compare optical clocks very remote locations, but this is a temporary technique. It's not going to last many years, so it's only a path towards the future technique. In the meantime, waiting for new time and frequency transfer, we try to take the best of existing techniques. And for GNSS, that may mean trying by just sheer number using all satellites from all GNSS available. There are now several tens of satellites up there, so we can gain a bit by using all what is available, but not so much actually. There are also advanced processing techniques, but using the intrinsic integer cycle nature of the ambiguity between the Carrier phase measurements of the different satellites. And we have shown with the BIPM IPPP techniques that this allows to go in the 10⁻17 level at a few weeks of averaging. So that's not yet sufficient to compare optical clocks, but that's a good move in the right direction. So to conclude, I remind that optical frequency standard now reach the 10⁻18 level, and that's a driver for the redefinition of the second. And the CCTF roadmap now plans for 2030 to present the new definition to the General Conference of Weights and Measure. And the reference timescale that the BIPM generates are now limited in accuracy to something like 1/10⁻16, partly because of the present cesium definition. And there are many challenges to overcome before the new definition takes place, and for UTCTI to fully benefit from our definition, and especially more operational use of optical clocks and better time and frequency transfer techniques. So I thank you for your attention, and I'm ready for some questions, if any.
Thank you very much, Gerard. I understand that there is no question in the chat box. Nevertheless, I have one query. I wonder that the signal from real VI can also be used for these standards. VLVI, you know very well, a very long wave interferometry.
Yes, there has been recent experiments of using very long baseline interferometry as time and frequency transfer technique. And this has achieved similar performance as the best techniques that we have now, that is about 1×10⁻⁻16. So it's not clear if VLBI can achieve a much better accuracy, but I guess that the experiments will continue in the next years. But we have to recognize that VLBI is not very simple to put into operation, and so it's a good technique to study, but it may not be easy to put into operation in any time laboratory at the moment. So we have to keep an eye on this, of course.
Sir, I'll have to another question. This is regarding the mention of optical frequency standards and its contribution to TAI. You mentioned about the optical lattices, but I suppose there are significant contributions also from the single ion-based optical frequency standards. Are we trying to get the contribution of those also when we plan for the redefinition? And I think they have, what kind of contribution do they have to the TAI right now?
Yeah, thank you. Yes, but that's a good question. Yes, I mentioned optical lattices because these are the kind of standards that currently contribute to TI. But of course, the single ion clocks are another path to optical standards. So they are considered also for further redefinition. Right now, we don't have any single ion clock participating to TI, but that may happen. Actually, there is one working group of the Consultative Committee for Time and Frequency, which role is to review the frequency standards that are allowed to contribute to TI. So any laboratory developing a frequency standard can submit its data for contribution to TI, and this will be reviewed by this working group and will be used when approved by the working group. So far, it has been only lattice clocks that have submitted data, but there is no a priori, nothing a priori against using single ion clocks.
I have one more question regarding the Davis mentioned. Just Davis mentioned E is equal to h nu and also E is equal to mc square. And then he derived at the equation of mass. And he said that it comes out to be 10⁻⁻40 kilogram. So I was wondering if that is the mass of one photon equivalent to microwave radiation of cesium atom 919263177 hertz. The mass of one photon, is it -40? And that leads to a new definition of kilogram in terms of mass of cesium transitional photon. So probably Davis mentioned that -40 number of in terms of kilogram. Is Davis there? He can also comment on it.
I'm here. This is a formal definition because you can't define any other thing as a kilogram if you have the Planck constant, the frequency of the atomic clock, and the speed of light fixed. You put them together and they make a mass, something that has the unit kilogram. So you can't define anything else as a kilogram. And so if you look at the experiments I showed to measure the Planck constant, they all trace back to a time. Well, you have to measure a time. The Planck constant is only measured to part 10 to the eighth. So but to do that measurement, you have to trace back to the atomic clock, which means you have to, that your time your internal clock, you don't need you have to trace, you have to be traceable to the definition of the second. You have to be traceable to the speed of light, actually, because you measure a velocities. For instance, in the Kibble balance experiment, you measure a velocity. Now, you can't measure a velocity in the SI. A velocity is some fraction of the speed of light in vacuum. That's the definition. You can't have another kind of definition of velocity. So you have to trace back to the speed of light. You have to trace back to the Planck constant. But you only have to do this to, say, part in 10 to the 9. Girard is talking about parts in 10 to the 16. It's not the limitation of the experiment, but you have to do it. The 10 to the minus 40 is real, but there are many tricks so you can actually get a kilogram without having to count 10 to the 40 whatever. Well, those things don't even exist. They're fictional. It's if the photon had a mass, what would it be, essentially, is the question. That's the question. So if that photon had a mass, it would be 10 to the minus 40 kilograms. But that's not how you realize the definition. In a short amount of time, I think that's the best I can do, unless there's a follow-up question.
Thank you, both of you. There is a question, but because of the shortage of time, and we understand that the third speaker, for him, it is already late evening. So I would like to start introducing the third speaker, Dr. Koji Ugeshi, who is a group leader of a Force and Top Standard Research Group, Research Institute for Engineering Measurements, National Metrology Institute of Japan, in the National Institute of Advanced Industrial Science and Technology, Japan. Dr. Koji has received his PhD degree at University of Electrocommunication in 1997 concerning the surface strength of the ceramics. After that, he has started his work on torque metrology at NRLM, the former NMI. He dedicated his research work fully towards establishing the traceability system of torque in Japan over the last 2 decades. He has published large number of the scientific papers and presented his findings in different seminars and conferences for many years. With this brief introduction, I have a pleasure of inviting Dr. Koji Ugeshi to deliver his talk. Dr. Ugeshi.
Thank you, Chairperson. Can you hear me?
Yes, please go ahead.
I'd like to ask the host to start my video file. I prepared video file according to the request from the teachers. Okay. Thank you, Chairperson. Good afternoon, everyone. My name is Koji Oguchi from National Metrology Institute of Japan, NMIJ. I sincerely celebrate that NPL India comes to 75th anniversary. Many thanks to Dr. Titas for giving me an opportunity to introduce the torque methodology in Japan. This is overview. First, I'd like to introduce the background of establishment of torque standard in Japan. Second, let me explain the present torque traceability system. Next, I'd like to talk about each traceability component. Then let me categorize the torque standard machines and torque calibration machines. Next, I'd like to explain our torque standard machines. On the other hand, let me introduce recent other topics of torque measuring techniques. Finally, I'd like to summarize my talk. Then let me begin with the introduction. As you may know, torque measurement is required for engine and motor test stands. Fastening torque is also important for the safety of building constructions. On the other hand, guarantee of precise torque measurement is required for office automation and audiovisual devices and fair trade. More than 20 years ago, ISO 9000 series, IATF 16949, ISO IC 17025, FAA, and FQA have been asking the traceability of measurement, in particular torque measurement, strongly. Then, demand for the torque traceability of torque measuring devices was increasing. 1997, a research project started for the establishment of the national torque standard in Japan. I was hired at NRLM, the former NMIJ, in this year as well. Recently, I heard that UL assessment and pharmacopoeia are also strongly asking the torque traceability. So I have dedicated myself into establishment of the torque traceability system for 25 years. Next, let me turn to the present status of torque traceability system in Japan. National Institute of Testing and Evaluation, NITE, has organized Japan Calibration Service System, JCSS, which accredits the calibration laboratories according to ISO IEC 17025. First, accredited laboratories of first grade make sure the torque traceability to NMIJ. Then they calibrate the torque measuring devices and reference torque ranges according to these guidelines. Next, second grade laboratories calibrate torque testing machines and torque range testers according to this guideline. Finally, third grade laboratories calibrate or test hand torque tools according to ISO 6789 or make sure various testings. Left side flow is for pure torque. Right side flow is for torque wrench loading. Next, I'd like to move on to explanation of traceability components. Here is a diagram of torque traceability system in Japan. I believe many countries and economies have similar systems. First, national standard in NMIJ. A national torque standard which is under the control of NMIJ The calibration equipment, which realizes precise torque loaded onto the calibrated torque transducer. It's categorized to deadweight type, force transducer type, and comparison type. Next, torque calibration machines. It's a torque calibration equipment calibrated by the torque standard machine using precise transfer standards. It's almost identical to the TSM, both functionally and structurally. It's generally the working standard for the accredited laboratory in the first grade, having function of the calibration for only torque measuring devices, for only reference torque wrenches, or for both TMDs and RTWs. Next, torque measuring devices. It's a complete set of torque transducer measuring pure torque, cable, and indicator. It becomes the superior standard for the calibration of torque testing machines and torque screwdriver testers. It also becomes the transfer standard for the calibration of torque calibration machines. It's categorized into the strain gauge type, electromagnetic type, optical phase contrast type, and so on. There are rotational and non-rotational, slip ring brush, and non-contact types. Next, reference torque wrenches. It's a complete set of the torque transducer with the form of torque wrench, cable, and indicator. It becomes the superior standard for the calibration of torque wrench testers. It also plays a role of the transfer standard for the calibration of torque calibration machines, which are able to calibrate only reference torque wrenches. Next, torque screwdriver checkers and torque wrench checkers. They are torque tool calibration devices without loading mechanism with only hand loading. In principle, they can be calibrated by torque calibration machines as torque measuring devices. Next, torque screwdriver testers and torque wrench testers. They are torque tool calibration devices with loading mechanism, enabled to hold the loading steps. In principle, they are calibrated by using superior reference torque screwdrivers or reference torque wrenches. Next, torque testing machines. It's an equipment which conducts material testing. There are also machines which test engines or motors. In principle, it's calibrated by using superior torque measuring devices. Finally, hand torque tools. They are hand torque wrenches and hand torque screwdrivers defined in ISO 6789, which is technical requirement for hand torque tools. Now, there are several accredited laboratories of JCSS in all grades. Then, let me move on to the categorization of torque standard machines and torque calibration machines. First, deadweight type. It generates the precise torque, loading dead weights at the tip of the arm. It makes sure the traceability for mass of dead weight, length of the arm, acceleration due to gravity. It must evaluate the sensitivity limit at the fulcrum. Almost all NMIs adopted this type as the national torque standard machine. Second, force transducer type. It generates the torque by using hydraulic cylinder or electric motor and an arm. At the opposite side of calibrated transducer, reference torque is measured by the output of force transducer at the tip of another arm. It's easy to realize in the huge torque regions such as meganewton meter using this type. The last one is comparison or reference type. A reference transducer and calibrated one are connected in series. Electric motor generates the torque with the braking system put at the opposite side. The output from the calibrated transducer is compared with one from the reference transducer. It's easy to be established, but it cannot be a primary torque standard. That means torque standard machine. Next, I'd like to turn to the introduction of torque standard machines in NMIJ. First, 1 kN deadweight type torque standard machine. This machine consists of pedestal component, weight loading component, arm component, bearing component for the fulcrum, aerostatic bearing, bearing components for counter torque, and installation component of the torque transducer. Here is the calibrated torque transducer. The calibration range is from 2 Nm to 1 kN. The relative expanded uncertainty of realized torque is 4.9 times 10 to minus fifths. Second, 20 kN deadweight type torque standard machine. This machine consists of the same component as the 1 kN machine. But we adopted and developed double aerostatic bearings for the fulcrum of this machine. The calibration range is from 200 Nm to 20 kN. The relative expanded uncertainty of realized torque is 6.6 times 10 to minus fifths. The last one is 10 Nm deadweight type torque standard machine. This machine consists of the same components as the above mentioned two deadweight machines, but this machine adopted a unique binary stack mechanism for the weight loading component. The calibration range is from 10 millinewton-meter to 10 Nm. The relative expanded uncertainty of realized torque is 6.4 times 10 to minus fifths. Let me summarize our torque standard machines. From 10 millinewton-meter to 20 kilonewton-meter, we can cover the torque range more than 90% of demand from Japanese industry. Here is the list of NMIs which had planned to participate to the CIPM key comparison in 2005. NMIJ has participated in both comparison of the range of 1 kilonewton-meter and 20 kilonewton-meter. Let me show you one of the results for clockwise torque at the step of 500 Newton-meter. NMIJ could show good results, as you can see. Another example for counterclockwise torque at the step of 20 kilonewton-meter. You can see the good results too. Then, here, let me introduce the recent torque measuring techniques. First is low torque or small torque. The demand for precise torque measurement in the range from micronewton meter to millinewton meter is being increased. Then NMIJ has developed torque standard machine with the principle of electromagnetic force utilizing the cable balance principle like this. Second is dynamic torque. Industry asks the precise torque measurement varying with time, but not average torque. They need to measure the torque variation in engine, motor, impact range, and so on. PTV in Germany has developed prototype dynamic torque standard machine, non-rotated vibration type. Here is the basic specification. Rotated vibration type torque standard machine is also under development. I have participated in this project as a guest scientist at PTV in 2013. Third is multi-component measurement. The industry needs to calibrate 6-component transducer precisely, or calibrate the screw testing machine having 2-component transducer. PTV has challenged to develop the precise 2-component force and torque standard machine, utilizing 1 meganewton deadweight type force standard machine. I have also participated in this work as a guest scientist in 2013. Finally, let me summarize my talk. Demand for the torque traceability of torque measuring devices from the industry has been increasing. Establishment of the SI traceability of torque is required. Of course, assembling all traceability of mass, length, time, and so on by yourself is also accepted. Torque traceability system in Japan was introduced. Many countries or economies would have similar systems. Components of SI traceability system of torque were introduced. Internationally recognized definitions of device may be required. Torque standard machines and torque calibration machines were categorized to 3 types. They were deadweight type, force transducer type, and comparison type. High-quality deadweight type torque standard machines were developed in Japan, and they are now being used for the dissemination of torque standard. Recent torque measurement techniques were briefly introduced, which were low torque, dynamic torque, and multi-component measurement techniques. Additionally, let me mention something about expression of values and units. Please read out the International System of Units, 9th edition. When percent is used, space separates the number and the symbol. 1% is not good. 1, a space, and percent is okay. Second, multiplication must be indicated by a space or a half-high centered dot. In the case of a torque unit, these expressions are all not good. Newton, a space, and meter, or Newton, centered dot, and meter is okay. Of course, you should put a space between values and unit. That's all. Thank you for your kind attention.
Thank you, Oguchi-san. It's a wonderful lecture talking about the torque traceability and the present torque standards, possibility of the very minute measurements of the torque, and so on. I just curious about, I do not work directly in this kind of the measurement. Why the kind of the system which is adopted in Japan is not being universalized?
Sorry, I can't hear you clearly. The voice is a bit small.
Sir, you can remove the mask, maybe. It will be clearer.
So I just wanted to first thank you, and then I just wonder that the your mention in your presentation, the system talk measurement system which is used in Japan, why it is being not universalized?
Sorry, why that, what did you say?
Why all countries are not adopting these kind
Okay, I understand. Many countries adopted the deadweight type torque standard machine. Yes, yeah, that's easy to establish the torque standard imprecisely by using the deadweight type. It's a same situation with a force standard. You know, force standard has many countries have a deadweight type force standard machine to realize the very precise force. It's a similar situation in torque. But if you keep the cost in the low level, you can adopt the comparison type or reference type of torque calibration machine. Some countries adopted such a comparison type. Yes.
Thank you very much. In the end, I would like to thank all three speakers who had narrated very exhaustively about three important topics in metrology. And I also like to take this opportunity to thank organizers for giving me opportunity to interact with the speakers, particularly Director CSAR NPL, Dr. Venugopal Achita. Thank you very much.
Thank you. Thank you very much.
So we come to the end of the first session of the Metrology Conclave 2022. Now I would like to invite on dais the session chair, Dr. Tiwari, and our director. Let's have a huge round of applause for them. I would request our director to kindly present the metrology clock, the customized my stamp, and the compendium as a memento to Dr. Tiwari. Thank you so much, sir, for coming here and sharing the session. Now we break for tea for 10 minutes. And after that, we'll have the final session of the Metrology Conclave. Due to shortage of time, we'll begin the second session sharp at 4 p.m. I request you all to gather here at 4 p.m. sharp. 95, MRSI Medal 96, and Indian Academy of Sciences Bangalore Medal, the National Academy of Sciences Fellowship, an Honorary Fellow of Punjab Academy of Sciences, and several others. He has been the chair of several important national and international committees and also published more than 200 papers. Let's have a big round of applause as we invite the session chairperson, Professor Arun Kumar Grover. Please, sir.
Thank you very much. Let me start by first conveying my greetings and congratulations to the NPL staff, students, and the alumni on the occasion of completion of 75 years of their dedicated service to India as a nation. In this session, we have 4 presentations. The first 2 presentations would be by the scientists invited from the National Physical Laboratory of UK at Paddington. Third one would be a presentation by a scientist from DIPM France, and last one would be the concluding remarks by the director. So our first presentation is titled The Kelvin Redefinition and Its Implications. This presentation will be delivered by a senior scientist from UK, namely Professor Graham Machin, who is the leader of Temperature and Humidity Group at NPL, UK. He has published over 240 papers. He has 30 years experience in thermometry research, and he has given numerous keynote addresses. He represents UK at the Consultative Committee for Thermometry, chairs the CCT Working Group on Non-Contact Thermometry, and the Task Group on Body Temperature Measurements. He was the president of the UK Institute of Measurement and Control. He chaired the Euramed Technical Committee on Thermometry, and he also received the Institute of Measurement and Control's Medal for Outstanding Contribution to Temperature Measurement. In 2021, he was elected Fellow of the Royal Academy of Engineering. Prior to it, he had been elected Fellow of the Institute of Physics and Fellow of the Institute of Materials and Control. The Institute had also awarded him Sir Harold Hartley Medal for outstanding contributions to the technology and measurement and control. So we are very happy. We have a very distinguished scientist from NPL UK to make this presentation on this momentous occasion. Welcome, Professor Graham. Welcome, sir.
Thank you very much for your kind invitation to speak, and thank you for your very kind introduction as well. I'll just share my screen. I hope that you can see that. Yes, I can see it on the screen. Yes. I just want to begin, first of all, by congratulating MPL India for achieving this outstanding milestone of 75 years of serving the Indian people and the Indian nation, providing reliable measurement. That's a really outstanding achievement. And I also want to thank the organisers of this meeting for inviting me to speak today. So I want to speak the next half hour or so about the Kelvin redefinition and its implications. And so the things I'm going to speak about are how the Kelvin are redefined. So I'm going to start my timer so I don't get lost in time. I'm going to speak about how the Kelvin was redefined, and then speak about the mise en pratique for the definition of the Kelvin. I'm going to speak about some current activities that are going on around the world at the moment, about realizing the redefined Kelvin, particularly at high temperatures and low temperatures. And then at the end of my talk, I want to give a future outlook looking at the impact of the Kelvin redefinition as well. So quite a number of things we want to do, and let's dive in. So first of all, how was the Kelvin redefined? So the Kelvin had this definition right up to May 2019. The Kelvin, the unit of thermodynamic temperature, as the fraction of 1/273.16 of the thermometric temperature of the triple point of water. It's a very simple definition. It's not, it's a quasi artifact. It's not like the mass, where there was only one artifact. Anyone who had access to triple distilled ocean water or distilled ocean water could make themselves a water triple point cell. So it was relatively straightforward to make. But in 2005, the International Committee of Weights and Measures fired a starting gun, as it were, approving in principle the preparation of new definitions of the kilogram, the ampere, and the Kelvin, and then shortly afterwards the mole was added as well. In terms of the Kelvin redefinition, that meant determining new values and low uncertainty values of the Boltzmann constant. And that recommendation really kickstarted global activity on how to determine the Boltzmann constant with low uncertainties. So this is our starting point. What is the definition, or what did the definition look like in terms of a Boltzmann constant? Well, this is what it looked like. The Kelvin symbol K is the SI unit. You can read that yourself. But essentially, the important thing was we needed to find what the Boltzmann constant was with low uncertainties and determine these two values, which at the time were not known with great precision. The only value that had these with low uncertainties was one measured by NIST in 1988, which Davis was involved in that, and it wasn't really a wise thing to do to base a redefinition just on one low uncertainty value. So a range of laboratories got involved in determining the Boltzmann constant. And these are the approaches, the main approaches that were followed for determining the Boltzmann constant. With low uncertainties, there was acoustic gas thermometry. You can see here the fundamental equations. I'm not going to go through them in detail. Dielectric constant gas thermometry, which is a capacitance measurement. Johnson noise thermometry, which is essentially measuring the Johnson noise through the random motion of electrons in a resistor. And Doppler broadening, which I'll come back to at the end of my talk, which is basically measuring the width of a spectral line and inferring the temperature from that width. And just acoustic gas thermometry, I should have mentioned, is basically measuring the speed of sound in a gas and determining the temperature from that speed of sound. In the redefinition, eventually these three techniques achieved low enough uncertainty, as you'll see very shortly, to redefine the Kelvin. There was two criteria for redefining the Kelvin set by the CCT and recommended by CIPM. And basically these two conditions were that the relative standard uncertainty of the adjusted value of the Boltzmann constant would be less than 1 part in 10 to the 6. That's to ensure there was smooth continuity between the old definition and the new definition, and that the determination of the Boltzmann constant should be based on at least two fundamentally different physical methods, of which at least one result of each should have a relative uncertainty of less than 3 parts in 10 to the minus 6. And at the time when this was set in 2014, this was a really challenging set of outcomes, particularly to get this very low uncertainty for at least 2 different methods. So when the final CODOR data adjustment was performed ahead of the redefinition, you can see here a lot of the data. And what's really exciting about this is you can see, first of all, that there were 2 laboratories, our French colleagues and MPL in the UK achieved uncertainties of less than 1 part per million with their acoustic gas thermometry. But there's also 2 other methods which have got uncertainty of less than 3 parts per million. There's dielectric constant gas thermometry by my colleagues in PTB in Germany. And then there's also Johnson noise thermometry here, particularly with NIST and a NIST and NIM, Chinese colleagues result here as well. So that was really exciting as well, which meant that in fact the CCT requirement or the CIPM of requirement for securing the Kelvin redefinition was really exceeded by quite a comfortable margin. The relative uncertainty was less than a half of part per million of the adjusted value. And in fact, not just two, but three physical methods actually determine the Boltzmann constant with less than 3 parts per million. So there was a very secure redefinition in prospect. And that enabled us to get these numbers, the 4.9, with very, very good uncertainties. And of course, now the uncertainty, this is now a definition, and this is the defined value. No one's going to measure the Boltzmann constant anymore. And any residual uncertainty, that 0.37 parts per million, was then transferred to the water triple point at the point of the redefinition. So this is now the definition of the Kelvin, which really should stand the test of time over the next decades, many decades, I would hope, as well. So how do we go about then turning that redefined Kelvin into a reality? How do we implement the redefined Kelvin? Well, the starting point is really the mise en pratique for the definition of the Kelvin. When the CIPM made its recommendation in 2005 to approve in principle the preparation of new definitions, it also at the same time approved in principle the preparation of mise en pratiques for the Kelvin, the ampere, the kilogram, and of course slightly later on the mole as well. And the mise en pratique is a really important document because it guides the user from the Kelvin definition based on the Boltzmann constant to a laboratory realization of the unit. And so it's really important because it's actually means there's a purpose. You're not just developing a standard and letting it sit there in the laboratory. There is a purpose in realizing the unit, and that purpose is, of course, to disseminate thermodynamic temperature or disseminate the temperature unit. But the mise en pratique allows dissemination of T rather than defined scales, as we'll see in a short while. Before 2019, temperature traceability was almost exclusively linked to the defined scales based on calibrations to the International Temperature Scale of 1990 or to the low temperature scale, the provisional low temperature scale of 2000. And temperature traceability was quite very straightforward. There was an unbroken chain of measurements, just like in many other traceability arrangements. There was the national reference that was then calibrated, that was then disseminated, to other laboratories through calibrated artifacts, and then the pyramids fanned out into user groups. And this is mainly guaranteed by third-party accreditation. But after the redefinition, this situation became more nuanced through the vehicle of the mise en pratique for the definition of the Kelvin. So the mise en pratique contains these items. There's the definition. There's a very important definition of terms, and particularly these two, absolute primary thermometry, where you actually can use absolute primary thermometry with no fixed points to disseminate T directly, or relative primary thermometry. You can use one or more fixed points with an explicit thermodynamic temperature to disseminate temperature as well. And both of those will be approached, as you'll see in a little while. Then there's some criteria for including thermodynamic approaches. There's some thermodynamic methods which can be used for disseminating, realizing, disseminating T, and then other things as well. But what's key is that the mise en pratique recommends that both the defined scales and approved primary thermometry methods for realizing and therefore, of course, disseminating the Kelvin can be used. And these are things like acoustic gas thermometry, direct and indirect primary radiometry, dielectric constant gas thermometry, refractive index gas thermometry, which is related to the latter, and Johnson noise thermometry, as well as the defined scales. I think also the mise en pratique clarifies that the ITS 90 and the PLTS 2000 do not give true temperature values. And that's a really important thing to keep in mind. They're very close to thermodynamic temperature, but they don't give them. And if you want thermodynamic temperature in physical equations, for instance, you need to use conversion factors. And these are available by approved annexes to the Mise en Pratique, or in fact as published values as well of T minus, T90 and T minus T2000, if you really want to get the true thermodynamic values in your equations. You've got more details about the Mise en Pratique. My colleagues and myself published this paper in the Philosophical Transactions of Royal Society. It's available for free download. And of course, the definitive Mise en Pratique text is available after the unit redefinition in May 2019, and you can download it from this website as well, web link as well. So what about some of the current activities in realizing the redefined Kelvin? Well, there's a lot going on, and I just really want to speak about two of them, one at high temperatures and one at low temperatures. At high temperatures, above 1300 Kelvin, and I think by 2025, we're going to see a real change moving away from the defined scale to actually having direct traceability to the redefined Kelvin. At the moment, we have basically the ITS-90. ITS-90 uses Planck's law in ratio form. You can see it on the upper part of the screen here. And here you have a black body, a fixed point black body of either silver, gold or copper. That is your reference starting point. It's a relatively low temperature. And then you use Planck's law in ratio form to extrapolate up to higher temperatures. And of course, that is the issue. You're using a low temperature and then extrapolation to high temperatures, and you can be prone to quite large uncertainties if you do that, particularly around wavelength definition or around nonlinearity corrections of your radiometer. So in early 2000s, maybe slightly before, high temperature fixed points were discovered and developed, and we're now using we now know the temperature of a number of these high temperature fixed points with uncertainties of very low uncertainties of maybe less than certainly less than 0.05%, around 0.02%. And by the end of this year, we're going to know the thermodynamic temperatures of high temperature fixed points, a wide range of them, another 4, again, with those sorts of uncertainties. So here you can use relative primary radiometry to set up a scale. If you want more information, you can turn to my review paper, which is a bit out of date now, but still has a lot of relevant information. So the intention would be to take the Mise en Pratique and use Planck's law in a parameterized form. So you can see here a simple Planck's law in parameterized form, and then use 3 high temperature fixed point or more if you want to use a least squares fitting approach of very low uncertainty temperature to set up a temperature scale which is actually truly thermodynamic, linked directly to the Boltzmann constant. And these temperatures, of course, have been determined by primary radiometry of various sorts. And by using this approach, you then have direct linkage to thermodynamic temperature. And there are some advantages in doing this. Basically, it's more robust than ITS-90. You're not doing an extrapolation to high temperature anymore. You can just do it over the temperature range you want. And what's really exciting is you can actually get National Measurement Institute type uncertainties down into the calibration laboratories. As long as they have a high temperature furnace, 3 high temperature fixed points and a suitable radiometer, they can actually generate uncertainties which are the same as the National Measurement Institute at the calibration laboratory. So that traceability link has then been moved to a calibration laboratory, and you end up with direct linkage to thermodynamic temperature. You don't actually have a link to ITS-90, or don't need a link to ITS-90 anymore. So I think this approach certainly has the potential to supersede the ITS-90 above the silver point by 2025 or so. So that's a really exciting development. And then at low temperatures, we're going to do similar steps. So think about low temperatures below 25 Kelvin, and a similar thing could happen in the late 2020s or so. At the moment, you can see that we have a very mixed state. We have the PLTS 2000, very low temperatures at 0.9 Kelvin to 1 Kelvin. We have the ITS 90, and then 0.65 Kelvin and above. So there's an overlap region where there's potential for confusion. And then there's different approaches. You can use vapor pressure scales. You can use an interpolating helium gas thermometer. You can use a platinum thermometer as well. And all these are different approaches to setting up ITS 90 or PLTS 2000, which is quite confusing for people. And actually, these are quite difficult to do, experiments to do as well. So there are very few national measurement institutes around the world that actually do these sorts of low temperature measurements, PTB being one of the few, but also LNE Canam does some of these as well, and our Polish colleagues. So what can we do about that? Well, we can, instead of having that complex arrangement, we can set up practical primary thermometry. We can use Johnson noise thermometry at low temperatures, which is reached a relatively refined state. There's primary magnetic field fluctuation thermometry, which is essentially Johnson noise thermometry, measuring the thermally generated magnetic flux in a noise sensor. You can also measure the mean square voltage directly as well. Or you can use Coulomb blockade thermometry. You can see here tunneling junctions, and the width of the tunneling junction depends on the actual temperature as well through this equation. So as long as you know the measure the width of the junction, you can determine its temperature. And then you can use acoustic gas thermometry as well above around 5 Kelvin or so. So you can use primary methods to do temperature realization and hence dissemination. So by the mid to late 2020s, you could see a Johnson noise thermometer, maybe the primary magnetic field fluctuation thermometer, maybe some other Johnson noise thermometer. You could use Coulomb blockade thermometry. You can use acoustic gas thermometry as well, all primary methods. So you'd have thought by the late 2020s, the ITS 90 and maybe the PLTS 2000 below the 25 Kelvin or so could be superseded and primary methods could be used. But what about the bit between 25 Kelvin and 1300 Kelvin, the bit where actually most people do their measurements? What could we do there? Well, let me suggest one particular approach. You could use acoustic gas thermometry, certainly from 25 Kelvin to 300 Kelvin. It's already relatively straightforward. It's already better than the ITS 90. So you could certainly use acoustic gas thermometry to provide that direct traceability to the redefined Kelvin. You can see here, for instance, this graph in the lower, my lower right-hand corner, this graph here, you can see here the consensus value of T minus T90. You can see the T90 deviates by around 10 millikelvin at around 150 Kelvin or so. And you see here that the T minus T90 values have been measured with very low uncertainty, much lower than the realization uncertainty of the ITS 90. So that's a really good approach. You could probably go up to 500 Kelvin or maybe even a bit higher as well with acoustic gas thermometry relatively straightforwardly. But it may still be that at the range between 500, 600, 700 Kelvin up to 1300 Kelvin, acoustic gas thermometry is too difficult. Maybe some other primary method, maybe even primary radiometry could be used for realizing the scale, or possibly a future temperature scale is needed with a limited range. We will see about that. And I want to talk about that in the last part of my talk now. What is the impact of the Kelvin redefinition for temperature traceability in the short, medium, and longer term? Well, in the short term, of course, we want about evolution, not revolution. In the short term, the current temperature scales will still be in use. The ITS 90 and the PLTS 2000 will remain the main ways of realizing and disseminating the scale, and they still are today. If you want thermodynamic temperatures, you can just use these published values of T minus T90 and T minus 2000. But in the medium term, by 2025, in the mid to late 2020s, I think it's very clear that primary thermometry will start supplanting the defined scales, particularly at high temperatures by indirect primary radiometry in the way I've described, but maybe even at low temperatures as well in 25 Kelvin or below, using Johnson noise or acoustic gas thermometry. And the PLTS 2000 may actually be supplanted before the end of the 2020s. So there's some interesting work going on there. In the longer term, the question is, will thermodynamic temperature truly and completely supplant and replace the ITS 90, or will the thermodynamic temperature continue to be used to around 600, 700 Kelvin, and then maybe a range restricted scale, the ITS 20XX, be needed to cover that difficult part for temperature traceability between 600, 700 Kelvin and 1300 Kelvin. Well, the CCT is keeping a very close eye on these developments, and we will see what happens in the coming next years or so. But in the last part of my talk, I want to speak about some very exciting developments which could link direct traceability to the Kelvin into industry, into the user community. And why this is exciting is it provides traceability at the point of measurement. And that's really a very important development. The sensor itself shouldn't need calibrating, or doesn't need calibrating. It's reliant on fundamental physics, and it's reliable over its entire range and while it's operating. The measurement system, the system that's used to measure the thermometer, will of course need calibrating, but the thermometer itself doesn't. And what this does is it actually breaks the concept of temperature traceability linked to an unbroken chain of measurement to the National Measurement Institute, National Metrology Institute. The temperature traceability comes at the point of measurement, and that's a real paradigm change in measurement. And we're working on a couple of these things now at MPL, both Johnson noise, and we're going to begin some work on Doppler broadening thermometry as well. In Johnson noise, of course, is based on the random motion of electrons in a resistor. It's a very small signal, and you measure the voltage, the mean square voltage. The bandwidth of the electronics is set by the electronics. The resistor is measured by independent means. This is the Boltzmann constant. So in principle, if you measure this, the temperature is the only thing that is unknown, and you can determine the temperature. And it's a challenge, of course, because the Johnson noise is of nanovolts. It's quite small. You have to reject all forms of electrical noise. And traditionally, these have been very significant metrology experiments requiring large shielded room, large amount of expensive equipment, each temperature measurement requiring several weeks, so not very practical. But we've been working with a small company who's very expert in using state-of-the-art electrical sensing approaches, and we've actually come to the point, not just us, but also I have to say my colleagues at PTB as well have also been working on this, and others as well, where there is actually a working practical Johnson noise thermometer. It needs more development, but the principle has actually been demonstrated clearly. And that's a really exciting development where you can actually put a Johnson noise in a measurement situation and give you traceability directly. There's still a bit more work needing doing, but hopefully by the middle of this decade, that will become commercially available. Doppler broadening is a bit more in its infancy. You'll remember this equation, but again, you'll see if you choose a particular species, the speed of light is of course known. This is the Boltzmann constant. If you measure the Doppler width of the actual spectral line, then the temperature is the only unknown in this equation. You knew the frequency at rest. You shine laser light through a cell, you measure the spectral width, which is broadened due to the thermal motion, and then you can determine the temperature. At the moment, it's a major physics experiment. It requires an optical table with lots of equipment on, and takes quite a long time. But you can do already, it's been demonstrated, very good thermodynamic temperature if you're very careful. Our aim, which is very ambitious, is to use a particular target or molecule, maybe an alkali metal, to miniaturize those gas cells. You can see here the gas cell is quite macroscopic, to miniaturize it to the size of a millimeter or a few millimeters, to develop a fiber couple system, and to demonstrate the principle of small scale Doppler broadening thermometry in the next 4 to 5 years. These are micro-machined silicon wafer gas cells that are used for magnetometry, for instance, but they could also be used for small scale Doppler broadening thermometry as well. So we have some work starting later in the year on that. And then really finally, I had this sort of vision, this dream. I'd like to sort of really see wide scale practical primary thermometry where you have temperature traceability at the point of measurement, no longer requiring National Metrology Institute intervention. These sorts of things are really important for Industry 4.0, for autonomous production, where you have a sensor embedded in a sensor network which is always on, always right, which can calibrate the other sensors in the sensor network. And this will really be important for facilitating autonomous production in the longer term. And that's really necessary so that we optimize our use of energy, that we make sure that we have industrial production that produces no waste, that it's always high quality, and of course that they, all importantly, greenhouse gas emissions are minimized through optimum use of energy. So a long work to do, and I think if you're interested in measurement as a young person, there's a huge amount of really interesting science to do in the next decade to make this vision into a reality. So I've come to the end of my talk. I've spoken about the Kelvin redefinition and how it happened, spoken about the mise en pratique and how that's going to govern temperature traceability in the next decade or so. I've discussed how the Kelvin redefinition has led to changes, or will lead to changes in temperature traceability from the National Measurement Institute, but also talked about the really exciting emergence of in situ traceability, and where you'll end up with traceability independent of the National Measurement Institute, actually built into the process itself. I've discussed some of these ideas in these papers down here if you're interested in reading more about them. So again, thank you for your attention. And if you've got any questions, I'd be very happy to answer them now, or happy to answer them by email as well. Thank you very much.
Thank you, Professor Graham. Are there any questions in the chat box? Please check. So there is one. Please go ahead.
In the Doppler broadened thermometry, what kind of gases or vapors do you propose to use, and what are the laser frequencies which will be used in the MEM space for small vapor cells and gases you talked about in the Doppler broadened?
Yeah, thank you for your question. To be honest, we are still working on deciding which ones we will use, but I suspect there will probably be, at least initially, alkali metal vapors, because you can get the density in there with a relatively small number of atoms, but sufficient to actually get equipartition between the number of atoms within there. The frequencies, as yet, I can't tell you those for now, but we know that there are lasers that provide the wavelengths that are needed to actually do those measurements. I'm sorry, I can't hear you without the microphone.
So alkali metals, basically rubidium or cesium at 780 and 852 nanometer?
Something like that, yes.
So thank you, Professor Graham, once again. So with this, we conclude your talk and we proceed to the second one.
Thank you very much.
Second talk. Title of the second talk is The Importance of Measurement Now and in the Future. And it would be given by Professor J.T. Jansen, who is the Chief Scientist at NPL Teddington, UK. Professor Jansen is a very well-known condensed matter physicist who had worked on magneto-optical properties of low-dimensional semiconductor structures in organic conductors, as well as he had also probed the superconductors and the strongly correlated electron systems before joining NPL in 1998 to initiate research in single electron transport to realize a quantum standard for electrical current. So he has progressed and he is currently he is distinguished for the application of quantum technologies, and he is also designated as an NPL fellow in quantum electrical metrology. His research involves a wide range of topics in metrology applications. He is a scientific co-director of the Quantum Metrology Institute, which covers all of NPL's leading-edge quantum science and metrology research, and it provides the expertise and facilities needed for academia and industry to test, validate, and ultimately commercialize the new quantum research and technologies. He was also elected Fellow of the Royal Academy of Engineering in 2021, and we are very happy that he consented to speak at our forum today. So over to you, Professor Jans.
Thank you very much for this kind introduction. Could you please play my recording of the talk?
Yes, please proceed with the recording.
Good day, everybody. My name is J.T. Jansen. I'm the MPL Chief Scientist, and I'd like to first of all thank the organizers for inviting me to this 75th anniversary of the National Physical Laboratory in India. And on behalf of MPL, I would like to congratulate your organization on this fantastic achievement. So today I will give a short talk about the importance of measurement now and in the future. This is MPL in the UK, in Teddington, where we've been based for almost 125 years now. And our mission of MPL has actually stayed the same for all that time. And our mission is for us to provide the measurement capability that underpins UK's prosperity and quality of life. And this has remained unchanged. It's still at the core of what we do, supporting prosperity and quality of life. But like any other metrology laboratory, we have to think about the future. We need to explore what new technologies and trends may change, why as a laboratory we need to do measurements, and how we need to perform measurements in the future. And this is really very important because it takes a long-term time for metrology laboratory to build up the capability to support the economy and quality of life. Now, predicting the future, of course, is very difficult. It's usually easier just to look in the past. So maybe we'll start off by looking sort of 15 years back. So who can remember 2005? Well, in 2005, this Nokia phone was the best-selling phone in the world. And this you can see from this phone. This was sort of a first-generation mobile phone. There were no apps, no sort of internet connectivity, and what you could do with the phone was very limited. So who could have predicted in 2005 that we can do all these things now on our mobile phone? We are fully connected. We can do as much as we can on the go as we can do in our office. Another important development was, for instance, Facebook. In 2005, Facebook had only 1 million subscribers. Today, it's about a quarter of the world population. And the whole sort of social media concept didn't exist in 2005. And now, of course, has changed the way we live our lives. We do shopping, connecting, working, everything through social media. So this shows you how quickly things can change and how difficult it is to predict that change. Looking a bit closer to home, the science highlights in 2005? Well, in 2005, John Hall and Ted Henge won the Nobel Prize for Physics for the development of the femtosecond comb technology. And today, femtosecond combs are used everywhere in time and frequency metrology. They are the workhorse of the laboratories, being able to connect microwave frequencies to optical frequencies with almost unlimited accuracy has been a tremendous step forward and will allow the redefinition of the second in terms of an optical frequency in maybe even a decade's time. Another highlight from 2005 was the development or the isolation of graphene, one layer of carbon atoms in a hexagonal lattice, which has got lots of very interesting applications. And one of the first things which was discovered in graphene was the quantum Hall effect. And I personally spent a lot of time studying the quantum Hall effect in graphene. And as it turned out, graphene has got a quantum Hall effect, which is incredibly accurate and very easy to realize with modestly low temperatures and magnetic fields, thereby making resistance traceability much more accessible for many more laboratories because it doesn't need very expensive and advanced infrastructure. But there are still many applications to come based on graphene, even though it's almost 20 years ago since the material was first discovered. It takes a long time for these applications and to be realized. So in 2020, we started a foresighting project at MPL to identify major trends in future society and industry. And we wanted to look at these trends and then analyze the trends and see what technologies are vital to enable them. And then we take one step further to see what the implications are there for metrology based on these technologies. Why do we take measurements and how do we take measurements? And that will inform us what we as a laboratory need to focus on, what capability we need to develop to address these trends. And we didn't just do a brainstorming session to analyze this. We used a proven methodology which is developed by the UK government, and this methodology is aimed at trying to avoid bias. So if I go and ask a certain group of scientists, what do you think the future will look like, it will probably very much confined to their experience in their field of science. So it's good to go very broad in who you ask opinions for. And also we wanted to have a diversity of views. So we didn't just go and ask very senior people in industry or academia, but we also asked very junior scientists, apprentices, people who've just done their PhD, and also non-scientists. What are their views about the future, and what do they think will become important? And from that, you learn an enormous amount. We collected for about half a year lots of information across. We trained a number of people at MPL to become horizon scanners. We interviewed a lot of people around the UK and internationally, from commercial backgrounds, from academia, from industry, generalists, specialists across the field. And we collated all this information and analyzed it and pulled out the main threats for the future. And we particularly looked at what are the drivers for change. And we identified three drivers for change. One of them is around well-being. We all like to live healthy. We all want to be secure and safe. And this has a number of challenges for a growing population and the way our social attitudes and values change. This is an important driver. The next one is sustainability. With a growing population, we want to reduce the human impact on the climate and our use and management of limited natural resources. So sustainability is the second big driver for change. And then finally, enterprise. Digital innovation really allows us to increase prosperity and productivity and growth, but also can lead to a more equal and fair society. So enterprise is the final big driver for change. Then in the middle of the project, of course, the COVID pandemic happened, and that was a very big driver for change. We stopped the project at that point and looked at what the impact of the pandemic is on technology. And of course, the pandemic accelerated many fields of science around health and life sciences, vaccine development. I mean, they really speeded up tremendously. What normally took 5 or 6 years to develop was now done in a couple of months' time. Other things, of course, which speeded up was the use of digital technology to continue to be productive. So we all worked from home, used internet and other sort of applications to continue to be productive, and those tools like Zoom and Teams, they were all developed much faster. We all did our shopping online. And there were some technologies and fields of application which slowed down. For instance, transport. Travel almost came to a standstill, and the aviation industry, of course, suffered very significant reduction in revenue, and thereby also a reduction of R&D and development of new transport modes. So we included those kind of developments also in our foresighting activities. So what are the top level outcomes of our foresighting exercise? Well, we've got 3 top level themes within our outcomes. The first one is around metrology to support digitally enabled global measurement infrastructure. The second one, big theme, is metrology to improve our understanding of complex systems. And the final one is metrology will give confidence in decision making. Those 3 themes are very generic, and in the next couple of slides I'll go in a little bit more detail explaining each of these. You can also, we produced a report which is on the MPL website. If you go to www.mpl.co.uk/foresighting, you can find all the outcomes of the report and also make contributions to that. So I encourage you to, if you're interested in this foresighting activity, to have a look at that. So let's have a look at the 3 themes in a little bit more detail. So supporting a digital enabled global measurement infrastructure. Well, the continued digitization of measurement allows us to shorten traceability chains and thereby reduce uncertainty. We, as metrology laboratories, we sit on the top of the measurement pyramid, where we realize the SI units and we disseminate our units through metrology labs, primary calibration labs, to industry measurements. Allowing to make use of digital applications allows us to bring these measurements much closer to the end user, thereby giving them access to the full accuracy of primary standards. Also, based on the redefinition of the SI, defining all the units in terms of fundamental constants, we can embed SI traceability directly into measurement instruments, thereby alleviating the need of coming back for traceability to a national metrology lab. And there is the ability to have in situ calibration of standards and local standards. And this, again, the devices which are calibrated once will always remain calibrated. So these are huge opportunities for the world of metrology, how we can really disseminate our standards through industry by making full use of the digitization of the global measurement infrastructure. The next theme is around improving understanding of complex systems. Metrology will support a systems-based understanding of the world. A lot of systems are complex, and I've used one example here of our climate. Is the archetypal complex system where we have the real climate on the left-hand side, and we make observations on that climate. For instance, try to measure the temperature of the Earth through climate data, and use these measurements to inform climate models. And these climate models, in turn, will inform climate policy, how we're going to respond to our global warming issues. And these lead to climate action, for instance, reducing CO2 emissions, which then, of course, have an effect on the climate, which we want to measure. So there's a feedback loop here. We want to see that the actions we take have a real effect on the climate, but there are many steps in between. And there's lots of data involved at each step, and data of different quality, of different provenance, on different timescales, which all need to be connected to get to a reliable answer about what's happening with the climate. And so metrology will have to support this in the future. And this use of indirect, hybrid, and proxy measurements will only increase in the future. And metrology will need to help to combine the data of different quality, provenance, and time periods. There's a lot of metrology to be developed for the future to understand these complex systems. Now, climate is not the only complex system which we can talk about. In a way, the human body and how the human body deals with cancer and the solutions for that are also complex systems, or systems in material science. There are many complex systems out there where lots of data will have to be combined, and that is going to be an important challenge for metrology labs in the future. And then the final one is around providing confidence in decision making. So metrology will support decisions made by machine learning algorithms and AI. So having all this digital enabled measurement data in complex systems leads to lots of algorithms being used to analyze this data and to make decisions based on this data. And how uncertainty propagates through these complex systems is something the world of metrology will need to deal with and need to provide solutions for. Agile and responsive regulation will enable automated decisions to be made, which is again coming to we generate so much data in the world that it becomes impossible to not use automated systems to use this. And that will rely on different ways of dealing with that. And then the final point there, measurement scientists will have the responsibility to ensure that data is being used with integrity and impartiality. Now, all through the pandemic, of course, we know how important the view of scientists has been through decisions which governments have to make. And it's important that scientists are impartial and explain the data to non-scientists in an understandable way. And there are many ways in which that needs to happen to give the general public confidence in the science, because our world is becoming so complex that it's almost impossible to make decisions without data. And for instance, the picture you see here on the bottom right is the analysis of, unfortunately, COVID death in England over time, measured with different types of methodologies. So using different days from when they were first detected. And you can see, of course, there's quite a significant change in the absolute value of numbers, which then informs politicians about what action to take. But if you use a different method, you get a different answer. And so scientists really need to explain very clearly about what it is they've measured and what it is their measurement actually means to the non-scientist. And I think all of us in the world of metrology, in the world of science, have got an important role to play in trying to make our science and the uncertainty in our science understandable to the general public. Otherwise, it will lead to distrust in science, which is a very bad thing to happen. So those are the three themes here in providing confidence in decision making. So the three overarching themes, just to repeat, a digital enabled measurement infrastructure. So digitization has become a very big theme in the world of metrology. The CIPM has developed a overarching strategy for how we're going to deal with this digitization around the digital SI, digital calibration certificates, how to deal with uncertainty in AI algorithms, how we store, retrieve, and reuse data, the so-called FAIR principles, is becoming a very big topic. And all this digital measurement infrastructure, of course, leads us to understanding complex systems. And then if you understand complex systems, you can use that understanding to inform decision making. So this is what we see as the three big themes in metrology going forward for the next decade or so. And NPL will be producing many more papers and thought pieces around this work on how we progressing with this. So with that, I want to leave you with a final slide about looking to the future, and a quote from Abraham Lincoln: "The best way to predict the future is to create it." And maybe another one from Dennis Gabor: "The future cannot be predicted, but futures can be invented." And of course, we as metrologists, we play a very important part in this whole picture of developing the future. And with that, I'd like to thank you for your attention, and I'm very happy to answer any questions on this topic. Many thanks.
Thank you, Professor Johnson.
Thank you.
Is there any question in the chat box? None? Anyone else in the audience wishes to ask anything? Yes, there is it. We have one question.
Sir, digital transformation, digital SI is the enabler for your whole work. The work which you have done, dealing with the complex systems also is based on the digitalization which you hinted upon. So what NPL UK has taken these steps, how are they transforming the measurement system? Are they only targeting the algorithms and the software and the validation, or digitalization of the measurement systems? What NPL UK is planning to do in this direction now, based on the work which you have done already?
Yeah, thank you for that question. Well, the digitization at NPL actually addresses all aspects of what we do. So all the way from automating measurements, making use of the new definitions of the SI, and implemented this, like Graham Machen explained, for temperature, incorporating that so that the SI can be realized away from NPL to the way we collect data, we store data, retrieve data, the methods we use in terms of our knowledge management of the data, and the analysis of that. So we are going through a whole process of digital modernization at NPL, both in the way we operate and in what we do. So it really is a very big piece of work, which is affecting almost every aspect of our work at NPL.
Is it also related to cybersecurity and the network infrastructure, network which you have created in NPL UK, and connection with the outside world, the communication link with the
Yeah.
outside people. Is it also linked with that?
Yeah. So one example is at MPL that we are working on a network of timing across the UK, where we take at the moment, of course, time is realized at MPL in Teddington, but this is, of course, not. This is a single point of failure. So we are building multiple timing centers across the UK, which are interconnected through various means, fiber links, GPS, and others, so that we have a completely distributed timing infrastructure across the UK. But then, of course, also all those other timing centers can be innovation centers for timing applications. So it's really taking the time signal out across the whole of the UK and thereby being a stimulator for innovation. And we'll hope to do that with many more areas of application.
So if there are no more questions, let's thank Professor Johnson once again, and we conclude the second talk. Thank you very much.
Thank you very much.
We proceed to the third talk of this session. And the third talk is titled Accurate Measurement in Support of Climate Action, Food Safety, and Laboratory Medicine. The talk would be delivered by Professor R.I. Vilgos, who is the Director of Chemistry Department at BIPM, France. Professor Vilgos, he is the Executive Secretary of the Joint Committee for Traceability and Laboratory Medicine, which develops and maintains an international database and review process for reference materials, method and measurement, services, in vitro diagnostics, sorry for the disturbance. Professor Vilgos is the Executive Secretary of the Joint Committee for Traceability and Laboratory Medicine, which develops and maintains an international database and review process for reference materials, methods, and measurement services in vitro diagnostics. And he is the Executive Secretary for Consultative Committee for Amount of Substance, Metrology in Chemistry and Biology, covering the fields of organic, inorganic, electrochemical, gas, surface, isotope, ratio, nucleic acid, protein, and cell analysis. Before moving on to BIPM, Professor Vilgos was a senior scientist at NPL UK. He had his degrees also from the universities in UK, namely the Cambridge University and the University of Bath, and he had worked at University of Ulm in Germany as a Royal Society postdoctoral fellow. So we are very happy that Professor Vilgos is here to share with us another dimension of meteorology science. Over to you, Professor Vilgos.
Thank you very much for that introduction. I hope you can hear me well.
Yes, sir.
Thank you very much. Okay, so what I'd like to do today is have a fairly broad topic to cover, which is talking about the application of metrology in three broad application areas. One is climate action, one is food safety, and one is laboratory medicine. And I hope I'll get across the progress that we made in these areas and the challenges that still exist for our community. So what I'd like to start with is to talk a little bit about metrology in support of climate and the Earth observation community. And we had a little bit of an introduction to that in the previous talk. So just to recap, BIPM's collaboration in this area, one of our major collaborations has been with the World Meteorological Organization. They're responsible for maintaining networks which allow weather to be predicted, but also essential climate variables which allow measurements which allow to predict how climate is changing. So our relationship with WMO goes back well over 20 years. We started working them within 2002 with a working arrangement. And then a very significant year was 2010, where we held a joint workshop with them to look at global challenges related to measurement challenges related to global observations and climate change monitoring. It was also the year 2010 where the WMO signed the CIPM MRA, allowing their central calibration laboratories that maintain standards for their observation systems to participate in the international comparisons organized by the BIPM. And that relationship, that working relationship has continued and strengthened. In 2015, we started to look in another workshop with the WMO about measurements of greenhouse gas emissions and measurements not only at the global scale, but the urban scale, which very much impacts most heavily on changes in greenhouse gas concentration. And most recently, last year, the CIPM, our management board of the BIPM, has set up a special sectoral task group to look more closely at the metrology needs in environment and climate change. And I'm glad to say that this year we'll be organizing a joint workshop again with the WMO, looking at metrology for climate action. I'll say some more words about that in a short while. So one of the areas, one of the examples where we made good progress in developing metrology to support central climate variables is that of the measurement of greenhouse gases. As we know, background greenhouse gases have continued to increase. And what we can see are, from the metrology side, key comparisons over 10-year time periods showing improvements in our ability to provide primary standards to support the measurements of these greenhouse gases, including carbon dioxide and methane, two of the major ones, but we've also got measurements of nitrous oxide and others. In fact, those measurements have become so good that they have been used to underpin the revision of the WMO scale that's used to measure background greenhouse gases and the types of background measurements that you see of the growing concentration of CO2 and the annual and the seasonal changes in those. And that work has continued as we start to look at measurements of greenhouse gases and mitigation of those measurements, meaning that more measurements need to be carried out, more standards are required, and these are standards that need to be based on scales and not just on SI traceability and how we actually achieve those. And we see groups being formed within the CCQM to try and address that. As I said, mitigation of greenhouse gases has been a growing area of importance for us and the measurements related to those. So back in 2010, we very much focused on the background measurements, but now we're seeing work and infrastructures being formed to set up global systems to be able to measure greenhouse gas emissions, which is based upon measuring changes in background greenhouse gases such as CO2 and inferring emissions based upon that. And we see literature being published on the compatibility of top-down and bottom-down processes to try and estimate emissions, and then follow on from those on looking at government decisions which impact on emissions and seeing how measurements can underpin and verify those political decisions. And some of the areas that we're looking at now is looking at standardized measurements, for example, of greenhouse gases in urban environments and the metrology infrastructure that's required to actually maintain those sorts of measurement systems. One of the areas where the BIPM and the NMIs have been heavily involved in this is, again, with CO2, the most important greenhouse gas. And an example of that, for example, is developing primary reference measurement systems for CO2. In this case, this is a unique system based upon manometry at the BIPM, developed with colleagues from US NIST and Sweden RISE, which is summarizing the equation you see at the bottom right, where if one takes CO2 in air and measures the pressure and temperature of the known volume, extracts the CO2 cryogenically, again warms up that CO2 and measures the pressure and temperature in a known volume, one can work out the mass, the mole fraction of CO2 in a gas provided that nitrous oxide is corrected for. And we can see, again, in recent years, the very good performance of those types of system with orthogonal measurement systems based on gravimetry produced by many of the NMIs around the world. We also see good collaboration with the environmental monitoring sector and how this type of standardization works interacts with the work of the WMO and how we can work together on using SI-based measurements to underpin the scales that are used for environmental measurement. Just to show some further information there is if we actually look at the comparison information in greater detail, we can see that the two measurement results, which are circled here in red, are the measurement results from the calibration laboratories that are effective in the WMO system. And we see the very, very good agreement of their standards with those of the NMIs. And in fact, that agreement was sufficient to help underpin a change in scale for all the background measurements of CO2 around the world that actually produced this curve of showing how background measurements change of CO2 in 2019. So again, a very nice example of how the SI traceable measurements, the NMI network, is underpinning global measurements of greenhouse gases. Greenhouse gases is not the only area where collaborations go on. There have been many areas. There's not enough time to go through all of those, but one should take into account that many measurements related to climate are performed these days by satellite. And again, there has been, back in 2008, we started by the community first developing quality assurance for Earth observation system, which had just been endorsed by the observation community in 2008. In 2010, what had happened is in the workshop with WMO, a large number of recommendations have been developed how to adapt and include quality assurance within the satellite monitoring systems. And we can see now that quality assurance system is widely accepted. A number of space agencies, for example, in Europe and the US, have applied that and referenced that quality assurance system. And a number of NMIs are actively engaged in supporting pre and post launch calibration sensors. And so very much we've been heavily involved as a community in helping calibrate instruments. And in the future, the focus will be more looking at some of the products related to climate, which are produced based upon those measurements and increasing knowledge upon those. So if you're interested in this particular area, I'm happy to announce that in September of this year, 26 to 30 September, the WMO and the BIPM will be holding another workshop looking again at how metrology can impact activities related to climate action. There'll be two themes on these. One is looking at metrology in support of the physical science basis of climate change and climate observations. And the second theme would be looking at metrology in support of greenhouse gas mitigation efforts. Pre-registration is already available for that particular workshop. So if you're interested, please follow the QR link here and you can pre-register and put down the areas of which you're most interested in contributing to. And we hope that this workshop will produce another set of recommendations on how metrology should develop to help support activities related to climate action in the 10 or so years in the future. So that's the end of my first section, talking about the area of metrology in support of climate action and Earth observation. I want to move on to another community that we support in the area of chemical metrology, which is that of food testing. So, of course, food is essential to all of us. And one of the areas that is regulated is that of potential contaminants in food because of their potential impact on health of our populations and also of animal populations. And one of the areas that we have been working in as a community in the NMIs is looking at measuring, producing measurement infrastructure to better measure mycotoxins in foods. So for those of you who aren't familiar with mycotoxins, these come from fungi, which grow on foods, usually in storage conditions which are humid. These produce toxins, which are harmful both to humans and to animals, either causing illness, long-term illnesses, or if the concentrations are high enough, death. And so these are very heavily regulated all around the world. So it's a food safety issue. It's also a trade issue because testing is required around the world, and test certificates need to be accepted when foodstuffs are exported, imported into a country for making sure that these types of contaminants are not present in any large quantities. So one of the areas that we've been involved with as a community is making sure not only that materials, methods and services agree measuring mycotoxins, but that these are available locally. And the reference materials that underpin these sorts of measurements can be produced and accessed at a local, national scale and do not need to be imported, so as to make sure that the costs remain low and these types of materials are used. So in measuring something like a mycotoxin, in this case, like for example, aflatoxin, we can set up a calibration hierarchy for that measurement. In the area of chemistry, that usually leads from the pure material to stock solutions, to calibration solutions, to the final measurement. And we have on this particular model the definition of the measurand, the types of methods that we use for measuring, and the types of reference materials that we produce. And one of the techniques, for example, at the top, as we start with the pure material, for example, aflatoxin, is something called quantitative NMR, nuclear magnetic resonance. Now, that's a technique that we've been developing quite a lot within the NMI community. The NMR technique, I won't go into great detail, but it basically allows you to link the intensity of the signal to simply the concentration of the hydrogen atoms on the organic material of interest, independent of the identity of that organic material. So using that, what you can do is measure the intensity of the signal. And if you have one pure compound internal standard, and you know how much you weighed into the sample and its purity, and you know another compound, how much mass it has and how much you weighed in, you can determine the purity of that second compound. So you have a system of determining the mass fraction purity of organic compounds really quite quickly and very simply with this sort of high accuracy system by making direct measurements on purity. Now, to make such a measurement, you do need an internal standard. And of course, we have hundreds of thousands of organic compounds to measure. So how many internal standards do you need? Well, certainly potentially more than one, because chemicals, first of all, are not soluble in all different types of solvent. Secondly, they can have peaks which overlap across the spectrum. And thirdly, they can react with each other. And so in a program together with the National Metrology Institute of Japan and a number of other NMIs, the BIPM worked on developing a system of 7 calibrants, internal standards that could be used as a universal set to effectively value assign the purity of primary reference materials of any organic compound that existed. And this is effectively what's been done and which is represented in this diagram with 7 particular materials available and now produced by NMIs around the world to help in developing traceable reference materials for these types of measurement. One of the other things that was done within this project was to make sure that the information related to the process of value assignment of such materials was publicly available. And for each of those 7 materials, we developed what we call internal standard reference data document, which allows anyone who wants to produce such material to already know the methodology for characterizing such materials. And this is an example of an NMR spectra for the type of mycotoxin material that we might expect, in this case, aflatoxin B1. And actually, this particular material, although it was supposed to be rather pure, had about 15% uncertainty, 15% impurities, which is a bias of 15% directly in a measurement, which is really quite important when you're trying to make a cutoff measurement. And so what in essence was done, that material was purified, and effectively what we did is also produce what we call guidelines on how you actually do the purity evaluation of such materials, and those are also publicly available for any NMI or any manufacturer wishing to produce such materials and such calibrants for use in measurements related to food safety and measurements of mycotoxins. One of the initial goals of this project was, as I said, to make sure that reference materials and calibrants could be produced locally and did not need to be imported. And that's really important to make sure that these materials and methods are accessible to the measurement community within or in individual countries. So it's not the fact that they were available in Europe that was sufficient. It would be important to make sure they were available in all parts of the world, since this is a common measurement problem and issue. I'm very glad to see that on the left-hand side here, you can see that as a result of the program, we have new reference materials being developed, in this case from Argentina, and we also were able to disseminate information about this type of measurement process and measurement standards through a number of workshops, for example, one in South Africa in 2018. And this program is continuing not only with some other mycotoxins, for example, ochratoxin A, which is a common contaminant in coffee and wine, but also moving on to pesticides and veterinary drugs, which are also rather big issues related to contamination of foods. So in my third and last example of the application of metrology, what I'd like to do is to give an example of how metrology is supporting measurements in laboratory medicine. So, laboratory medicine. If you're feeling unwell, you would probably wish to go to your physician, to your doctor, and describe your samples and hope for a diagnosis. That might involve a description of how you're feeling, a physical examination, imaging, but also samples may be taken and sent to the laboratory for testing. And this is what we mean by laboratory medicine. So when samples are taken from you, they would be sent to a medical laboratory. This could be in a hospital, but it does not need to be. And those laboratories tend to use large, modern instruments for making many measurements, tens of thousands of measurements and samples a day, with instrumentation that is produced by in vitro diagnostic manufacturers. Of course, that measurement needs to be calibrated, so there are calibrations and calibrators involved, and those need to be value assigned by calibration or reference laboratories using reference measurement procedures, which themselves have been calibrated using certified reference materials, for example, from national metrology institutes. Now, this is an area that's regulated, and one example of such regulation is in the European area, where quite a well-known regulation exists for in vitro diagnostics, called the In Vitro Diagnostics Directive or regulation. And I'll come on to some specifics about that and why that particular regulation is quite revolutionary. But it does require the manufacturers to use traceable calibrators in establishing their measurement system. As I said, because this area is regulated, there are also harmonized standards describing the technical requirements of the traceability and the reference measurement procedures and methods. And you can see the various numbers that are given there. Those are developed by ISO TC 212 working group predominantly. And what I'll go into a little description is what was the involvement of the metrology community in this whole area. So the concept of measurable traceability is well understood within clinical chemistry and laboratory medicine, and is based on starting with reference methods, reference materials, and reference measurement services. As I said, the regulation that appeared in Europe in 1998 was quite revolutionary because it contained this one phrase which talked about the traceability of values assigned to calibrators and or control materials must be assured through available reference measurement procedures and or available reference materials of a higher order. And that means a higher metrological order. So the first question that industry asked, IVD industry asked when they saw this regulation, what are these materials and methods that we need to be traceable to continue to sell our products within the European market? And that's exactly why the BIBM BIPM, together with a number of other international organizations, set up what we call the Joint Committee for Traceability in Laboratory Medicine. And this was set up by the BIPM, by the IFCC, the International Federation of Clinical Chemistry, for the ILAC, representing the accreditation bodies, and most recently, the International Committee for Standardization in Hematology. What this committee has done and continues to do is to maintain a quality assured database of higher order reference materials, methods and procedures, and a process for reviewing those and publishing those in the database, as well as an education site on traceability in laboratory medicine. So that particular database, which is one of the only database that BIPM maintains currently, which is very much sector-based as opposed to the key comparison database, contains about 700 entries with about 200 to 300 materials, methods, and services, all of which can be used by IVD industry to assure this essential requirement for traceability, and in so doing, ensure comparable measurements from different manufacturers in different hospital laboratories and different clinical medical laboratories for the same measurand. So rather than go through the database in detail, what I'd like to do is to give you an example of a particular set of measurands and the information contained about those in the database. And I'm choosing the example of measurands which are related to diabetes. So diabetes is a disease which is very widespread around the world. Recent estimates make that at least 500 million people suffer from diabetes. There's some numbers here from the UK and the US, but there's no country that's untouched by diabetes. And from the measurement point of view, there are a number of biomarkers that are measured related to diabetes, both in terms of diagnostics and monitoring of the disease. And those include glucose, HbA1c, glycated hemoglobin, and C-peptide. And all of those have well-established traceability and calibration hierarchies. What I'd like to do is just explain a little bit using the simplest example, which is glucose and glucose measurements. So this is an example, a simplified example of a calibration hierarchy for the measurements of glucose in human samples. We start at the left-hand side with defining measurement procedure to define purity for pure material glucose, the measurand that we're measuring. We can then make a certified reference material, prepare a calibration solution, a primary calibrator, which is then used to calibrate, for example, a mass spectrometric method based on isotope dilution to then measure glucose in a serum sample. That serum sample needs to resemble human samples because it needs to calibrate kits which effectively do measure similar samples. And within the manufacturer's system, there's a hierarchy of measurement systems, which then effectively produce more calibrants, which are effectively used to calibrate the end product instrument, which is used to measure the human sample. So this is another simplified version of that same calibration hierarchy, this time horizontally. This time vertically rather than horizontally. And again, we go from the pure materials to calibration solutions to the human serums, so the serum samples, which are reference materials to actual measurements. And if we look at the database, we can see that, for example, IVD industry would be able to search that. And for example, at the top of the chain, be able to find reference materials, pure reference materials of glucose, for this time produced by the National Institute of Metrology in China, which can be used for calibration. Going further, and the question is, how can we know the quality and have confidence in the quality of the values assigned to that reference materials? Well, within the CCQM, we organize comparisons of purity against, again, here using the quantitative NMR technique. This is a comparison, not of glucose, but of valine, which is a very similar type of molecule, at least in terms of size and polarity, from which we can infer performance to glucose. And we can see the very nice results of NIM, giving confidence in the ability to value assign such materials, such as pure glucose. If we go further in the calibration hierarchy, the next step is a primary reference procedure for measuring glucose in serum. And again, if we search the database, we can find a number of methods which have been reviewed and published, which can be used and followed to make that measurement method. And we can see the concentration range and uncertainty available for those. Those can then be applied by laboratories that produce reference measurement services. Again, those are listed in the JSON database, who actually value assigned samples, which, for example, can be sent from industry, which they can use as higher order calibrators in their system. You can see the performance characteristics of two of those measurement services for glucose in serum. Again, how can we have confidence in those reference measurement laboratories? Well, if we look at the international comparisons organized by our colleagues in the IFCC and the RELA scheme, this is the result of measurement of glucose in serum samples. It's two samples, blind samples sent to the laboratory, and so you have a Uden plot with results on two axes. And we see really very good agreement for those types of measurements within the stated uncertainties. So we have confidence in the application of those reference measurement procedures. Finally, moving down, the next area is to have a reference material, which can be a commutable reference material, which can be in human serum, which can be used for calibration of kits. And again, we can see in this case that we have an example of such a material produced by the French National Laboratory, LNE, again, with concentration range and uncertainty it's produced with. And again, we can have confidence in the values assigned to those materials, this time through the CTQM comparisons, not on pure materials, but on materials in human serum samples, glucose being one of them, but a number of those being carried out on a regular basis. And finally, when we move, most importantly, to measurements of human serum samples, human patient samples, we can again look at the performance and proficiency testing schemes for laboratories actually carrying out some samples, and we do get very good agreement amongst those screens. And so we do get to the final product that we wanted, which is good agreement on human samples through the application of traceable calibration hierarchies through different IVD manufacturers. So a system that's working well. Well, what are the future challenges in this area? Of course, glucose is only one analyte of very many analytes to measure. Estimates of analytes do vary. There could be 700 biomarkers, but it could be also 7,000 biomarkers, depending on how you define what is an important major biomarker to measure. And so that remains a challenge for the NMIs and the community going forward, which measurands to prioritize and to standardize, because it is a major process to do so. And new biomarkers come along quite often. And for example, we can see that a recent example being SARS-CoV-2, and this is an area where, for example, the NMI community reacted very quickly to start standardization of activities, and there were key comparisons, pilot studies under CTQM carried out, both for SARS-CoV-2 RNA copy number and also for SARS-CoV-2 monoclonal antibodies to underpin measurements both of viral content and also of antibodies in these areas. So you can see that that's a continual challenge for the NMI community going forward. I'd just like to finish up by saying that in the area of health, last year, the World Metrology Day theme was measurement for health. And if you'd like to learn more about traceability and measurements in laboratory medicine, the JCTM released a series of videos. They're available on the BIPM website, which describe in greater detail measurements in metrological traceability for laboratory medicine. So please feel free to look at those and find out more about those activities. And with that, I'd like to thank you for your attention and that ability to provide you an overview of a number of activities in three major sectors. And I'd like to wish you and congratulate you again on your Jubilee celebrations. Thank you very much.
So thank you, Professor. So we have enough time for questions. Is there any question in the chat box? No question in the chat box. Anyone else? So may I ask the director, NPL, do we have adequate?
Good evening, sir. Just I want to know regarding the traceability establishment in mycotoxin in food material. Is it enough for using an internal standard and adopting a established method? So it is enough for establishing traceability or some more things is required?
So the traceability hierarchy goes to the pure material in the case of the mycotoxin. One of the challenges of mycotoxin are that these are naturally produced materials. So in the first case, the impurity content can be actually relatively high. And so that can impinge the bias on these measurements. So one of the focuses of our programs has been on helping NMIs who are developing programs in this area to develop the methods for the pure materials and the calibrants. But a number of our NMI colleagues, especially in NIM China, but more recently also in NRC Canada and South Africa, have been developing programs to help NMIs develop matrix reference materials of aflatoxin and various foodstuffs to help them either as calibration or validation tools for those types of measurements for industries and testing laboratories in their countries. So I hope that answers. And that program is ongoing. So if NPL India is interested in participating in that, please have a look at the website and participate. And those courses are now online, which allows us to reach a much wider number of participants amongst the NMI community.
Okay, thank you. Right now we don't have QNMR, but our sister laboratory is having, and which is already accredited for 17034 also. So we can think about this. Thank you so much.
So for the QNMR, so the internals, all the information on the use of the internal standards from the QNMR is available on our website. And a number of NMIs who have been active in that project have developed those internal standards, which are available as CRMs. So if you're interested in that, I can certainly direct you towards those particular NMIs that are producing such CRMs.
Okay. Thank you so much.
You had one?
Yeah, I have a very naive question regarding the pre-calibration of the sensors which are used in the satellite payloads by different space agencies across the world. So is it related to any reference material, this calibration of the sensors? And then also you mentioned that there is a requirement to post-calibrate them, so is it done remotely? How the post-calibration of the sensors in the space happens?
Yeah, so that's not the area of my immediate expertise. So I would certainly be able to direct you to my colleague at NPL, Emma Williams, who's much more involved in that particular area of calibration. But yeah, both pre and post calibration are involved, and there are services from both those laboratories.
Thank you.
Anyone else? Please hold up.
Yeah, Dr. Roberts, thanks for your very interesting talk, and thanks for accepting our invitation to be speaking in this session. So actually, this extension of the question which my colleague Dr. Ashish has asked. We do have a lot of issues now related to the sensor-based measurement systems, both for air quality and also the climate change issues also. Increasingly, people are trying to use the sensor-based measurement systems. And so we don't have any mechanisms for a kind of certification also. Our regulatory agencies are also struggling with that, and they want us to help them. So is it BIPM doing something in that respect?
So we're not doing something directly, but one of the topics in the workshop currently being considered on greenhouse gas mitigation is looking at low-cost sensors and sensor calibration. So I think that would be the immediate place where we would focus our attention. Although this is a topic that comes up quite often, is whether there are such things as low-cost sensors that can provide you with accurate measurements, and how do you fulfill the calibration and testing requirements. So I think the most immediate area where we will address this probably in our September workshop in one of the subtopics and the themes about greenhouse gas emissions.
Thank you.
Is there any other question? One more. So with this, we conclude the first three talks. And to move on, may I now invite the Director NPL, Professor Venugopal Achanta, for his closing remarks. Professor Achanta joined as Director NPL 6 months ago. Prior to it, he was a faculty member, a professor at Tata Institute of Fundamental Research. It is the same institute that he had joined for a PhD 25 years ago. After obtaining his PhD from Tata Institute of Fundamental Research, he had gone to Japan, and there he obtained a PhD in electrical engineering and worked there and for a few more years. And he was inducted as a faculty member at TIFR in 2004. And he is well known for his work on the design and demonstration of an ultra-fast all-optical switch. At TIFR, he had worked both in the area of theoretical physics as well as doing experiments on semiconductors. And I was particularly happy that he chose to accept the directorship at NPL. I was a colleague of his at TIFR for many decades. And it's just coincidence that I'm serving as the chair of the Research Council when Dr. Achanta arrived to serve as the director NPL. So over to Director NPL, Professor Achanta Venugopal.
Thank you very much, Professor Grover. I would like to thank each one of our speakers today, Dr. Richard Davis, Dr. Gerard Petit, Dr. Koji Oguishi, Professor Graham Machin, Professor J.T. Jansen, and Dr. Velgos. We are very thankful to you for accepting our invitation and participating in this memorable event for us. We look forward to have more interactions with each one of you in near future. And thank you once again. So I'll stop with this.
I hope the colleagues at NPL, in particular the younger scientists at NPL, got an exposure to the frontiers of metrology, at least in institutes in Europe and Japan. We couldn't reach out to NMIs in other parts of the world because the timings are not favorable for inviting speakers from US or South America. So it was just a half-day conclave, but it did give an exposure to what the frontiers of metrology are at the peer institutes globally. So hopefully the younger people are able to see the gap between the level at which we are operating and the peer institutes at the frontiers are operating. There are obviously some gaps, and we hope that these gaps would get covered in decades to come. And the NPL will use the occasion of the 70th completion of 75th year to draw up a vision document for them in which the different divisions of NPL would give their projections for next 10 years as well as for next 25 years. We need a short-term vision document as well as a long-term vision document aimed at reducing the gap between the performance. Of course, some of our performance has to be related to issues within our own country. They would be different from the issues faced by scientists in Europe or America. So we have to address to our local needs, but we have to be continuously competing at the
international level because scientific research per se does not have national boundaries. So it's an occasion to have an assessment of ourselves vis-a-vis the frontiers at the very top. So hopefully in a year from now, we would have such vision documents ready, and we would start working on those visions on the short term as well as on the long term. So I hand the mic back to the Director NPL if he has any final comments to make.
I think that you have put it well. So we'll work on the vision document. We'll take help from our peers and other NMIs whom we are in touch with. Come up with the vision document so that we can perform better. Thank you. Thank you, everyone.
Okay, I would like to thank our RC Chair, Professor A.K. Grover, for conducting this session successfully and for being part of our celebration, this Platinum Jubilee celebration. So now I would like to request our RC Chair to come to the dais, and I also request our Director, Professor Gopal, to come to the dais. Please. So I would like to request our Director, Professor Gopal, to present memento to our Professor A.K. Grover as a token of appreciation for having come and being part of our celebration and grace this occasion. Thank you very much. Thank you very much. With this, I would like to thank all the participants, all the audience, all the presenters for having being part of this Platinum Jubilee celebration of NPL and having come and grace this occasion. Thank you very much. With this, the event for this day has come to an end. Tomorrow again, we will be having other events. I request you to join. Thank you very much.
Recording stopped.